Welcome, everyone, to the Cartesian Cafe today. We're very lucky to have Grant Sanderson with us. Grant Sanderson is a mathematician who is the author of the famous YouTube channel 3 Blue 1 Brown, viewed by millions for its beautiful blend of visual animation and mathematical pedagogy. His channel covers a wide range of mathematical topics, which, to name a few, include calculus, quaternions, epidemic modeling, and artificial neural networks. Grant received his bachelor's degree in mathematics from Stanford University in 2015, and he has worked with a variety of mathematics educators and outlets, including Khan Academy, The Art of Problem Solving, MIT OpenCourseware, Numberphile, and Quanta Magazine. Welcome, Grant. How are you doing today?
I'm doing well. How are you doing, Tim?
Good, good. Uh, I thought maybe we just start out by asking a little bit about you. How did you get interested in mathematics and ultimately using that inspiration to become the mathematical artist that you are today?
Interested in math. I mean, it depends on how deep you want to go, but I was definitely one of those kids where, from a very young age, I self-identified as liking it. I think a lot of that probably had to do with games that my dad would play with me. That like a lot of dads, just wanted his kids to be interested in science and math and the world and things like that. And I just loved patterns. And I think you can get into positive feedback loops in the current education system that, like, for those who are doing well is like self-validating, where you perform well, you think, oh, this is something I'm good at. So you like to think about it more and then you perform well and that kind of thing. And so I think a lot of the early relationship with it was maybe less pure in that way, right? It's more tied to a system around it. But, by the time I was a teenager or so, then I got more interested in some of the beautiful sides of math. And I remember there being one particular calculus teacher I had who made an effort to, like, go above and beyond. And aside from the topics in the class itself, he would lend me books like The Art of Problem Solving, or told me about this event called Math Circles, which I didn't know about, but of course they're all over the nation. And there was one at the University of Utah that I started attending. And there, they'd bring in guest speakers, typically mathematicians, talking about something that is accessible to a high schooler, but not at all in the straight line path that you typically see there. And so, that continued. I was even more hooked. And by the time I was going to university, it's kind of no question. I'm like, all right, I know I'll be a math major. Um, Although I did get pretty seduced into computer science along the way, but ultimately stuck with math in the end there. Um, and yeah, there's just a lot of little things kind of adding up along the way.
Hmm. Yeah, I mean, obviously your path is very unique. When I guess everyone has a different maybe idea, or maybe not even always a well formulated idea of what they're going to do with math. For some people, it's like, I want to become a research mathematician. I already know that I'm going to go to graduate school, get my PhD, etc. In your case, did you have such a vision, or what was like the end game, so to speak, insofar as a high schooler can have sort of that notion?
I don't know if my high school self would have, other than like having been fascinated by the fact that mathematician is a thing and thereby thinking like, oh, I want to do that. I think I always enjoyed teaching and exposition and that kind of thing. So I was drawn to the idea of like being an expositor, right? The Steve Strogatzes of the world, where on the one hand, yes, they have their research portfolio, but they also spend a lot of time, um, giving talks, writing books, things like that. And there's no path to that per se, but it seemed pretty clear that if you want to do that, you become a mathematician, you do the PhD, be a researcher, kind of do all that. And so I think in the back of my mind that was maybe the plan. Also, as like a potential fork in the futures, as I got more seduced by computer science, I was like, yeah, actually, the world of joining startups and building things there seemed equally enticing. Um, but by the time I was graduating, my tentative plan was still to get a PhD and kind of go down there. But um, given that the end goal is one of exposition and that kind of position where it's almost like the research would be a means to the end. Um, I felt pretty optimistic about the growth of the internet and like a little bit more pessimistic about the growth of positions in academia. Um, and I knew, okay, I kind of want to do something that's not in academia for like a year or 2 years between, graduating and PhD programs, which is not typical in math. Like gap years are not really a normal thing that one does, which I don't understand why, because it seems really healthy to get your head out of academia in some way. I ended up spending that year at Khan Academy, on like a fellowship program where I was basically making multivariable calculus content and some other odds and ends thing. And in the background of that was doing what is now 3Blue1Brown and that kind of channel on the side. And basically stars aligned such that that grew more than I was expecting it to. And it seemed to make sense to maybe just devote my full efforts to that, where rather than the professorship as a means to the end of being a public expositor, I'm like, maybe you can just go with the internet from the ground up. And as long as the material is like well researched and like it doesn't need a credential behind who I am to justify itself, as long as the content itself justifies itself, maybe that can work. And that's kind of the beauty of the internet and YouTube. It's also maybe a little bit of the tragedy of it, or it's a risky thing where you don't necessarily need to be the expert in order to have the things go out that are like widely viewed and such. But I think generally audiences are pretty good at discerning what's trustworthy and what's not. But slowly as the years went on, the thought of like doing the traditional PhD path, which I still haven't completely ruled out. It's just that at every given moment, it's like the opportunity cost is just too much. Yeah, it just kind of like wanes and wanes into the background.
Yeah, well, I'm glad that the going off the well-paved path clearly paid off for you. And actually, I think that it's a good transition to the next question I want to ask you, which is where do you kind of maybe see math pedagogy going given the role of technology? So math is a very old subject, and it's still taught in universities more or less the way it was taught, I don't know, centuries ago, lecture, blackboard style. Of course, recently we've had innovations, there's I think maybe Khan Academy was the first to maybe kind of take advantage of YouTube and sort of maybe the virtual format, and then it became MOOCs. Of course, you came along. My podcast is its own innovation in terms of trying something different, conversational mathematics with the technical substance with using a whiteboard. And now we have AI doing automated theorem proving, the big tech companies, Google, OpenAI, DeepMind. They're at the point where they could start solving Olympiad style problems. And, within the next few years, it's only going to get better. Do you have any thoughts about the role of AI and technology in terms of where math education might be going?
I guess there's a lot of different things you hit on there. One of them is the contrast between traditional Blackboard lecturing and alternatives. One of them is the role of something like YouTube that is able to broadcast out a lesson in like a asynchronous way to a large number of people. And then the other one is the role of AI in this. Hitting them one at a time. I think with the lecture format, I don't think technology is the right solution there. Like culturally, you just want something that supports more of a conversational, reactive to the listener dynamic, where that can maybe pair together with the second one of broadcasted things. I am an advocate for the flipped classroom model if it's done well. It's easy to do poorly, but in principle, the idea of spending time with the professor or the teacher or whoever it is more actively, where that's when you do your own exercise and homework with guidance from them, rather than when you're passively consuming lecture material, and instead let the passive consumption happen on your own time, where you're only ever going to a lesson right when you want to know it, and you're able to look for the best person in the world for you to explain that. What that implies is that the more content online, the better, and the better curated it is, the better. And also that there's going to be a benefit from filling in that gap between the introductory things that are going to reach a large number of people because that's what they're searching for, and then the things that are 12 lectures into such and such course, right? Where at the moment you're going to be able to find like a million Python programming for beginners videos out there, right? But you're going to not find a lot that are targeting the person who's like 2 years into a learning trajectory on a very specific path. But the more you can fill out all of those, the more possible it makes it to flip, or at least partially flip classrooms. And then on the front of AI and theorem proving, that feels at the moment very independent of education, because I don't know if you've ever like looked at the kind of outputs of the proofs that they'll have and things, but it leaves a lot to be done by the human to explain what was going on. And there's a pretty big difference, I think, between a proof and an explanation, like a proof of why something's true, and then a deeper understanding. Even when humans are the ones to generate the proofs, you see this in the context of whether someone's writing a publication that's meant to be showing why something is true versus if it's deliberately meant to be more expository. And, the role of theorem proving, it's going to be fantastic, but I think it leaves a lot of sweeping to be done by the expositors to go behind it, say like, okay, this is a thing that's true. What's the moral reason why that should be true? Maybe with large language models, you also get something closer and closer to that. But it feels like by the time you have something that can automate the exposition side of it, like really resonating with the human to say what will make this understand well, um, it's hard to imagine a task that's harder than that, such that it doesn't require AGI to get to that point. And then once you have AGI, you're in such a different world anyway that it feels silly to
Mm.
be asking those questions.
Yeah, I imagine. Although, yeah, I guess this is probably be a topic for another conversation. But given that AIs can generate novels, I imagine, you take that kind of artistry and combine it with the rigor of mathematics. Maybe they can also generate beautiful expositions as well. Who knows, right? That's
Yeah.
conceivable.
Have you ever enjoyed an AI novel though? Like it's very easy. It's not easy, but it's like quite possible for modern AIs to produce stuff that feels a certain way. It feels really consistent with what you would expect of a novel and all that. But then if you step back and ask like what are the deeper themes? I I don't know. I think there's a really big difference between good writing and bad writing. And you can just have a lot of things that's like fluff that sentence by sentence like feels quite good. But the
Mm.
ones that are actually putting out new ideas that are done so deliberately, um, and it's not the case that AI like can't do that, but it's a notably harder task, I think. And I don't think we're quite there yet. But yeah, to your point, once you are there, once you're able to uh, legitimately write in a way that doesn't sound like Dickens, but that like thinks like Dickens, then you're probably also there in a way that can actually explain math rather than just proving it. And um, who knows? Who knows?
All right. Well, why don't we actually start diving into mathematics then? And of course,
Sure, sure.
well, we're not AIs. We're actual people. So hopefully, we'll do a decent job of explaining the mathematics. So today's topic, we're going to talk about the unsolvability of the quintic, and there's a lot behind that in terms of the history, the problems leading up to that, the theory that was developed to solve it, Galois theory. Um, do you have any comments about why you're interested in this problem, how you think about it, maybe just to give a kind of a big picture overview before we just dive in?
I might give too big a picture. The long story short is that I was interested in a certain video topic last year that had to do with a very different proof of this fact given by Vladimir Arnold that's topological in nature, came in 1963. I might still make a video on it. One of the reasons I might not is that a contest that I ran last summer included a submission where someone did a pretty beautiful video about it. And I'm like, okay, in some sense, like there is already a nice video. I could see other ways I might go about it. But that got me thinking a little about why do we care about the problem? What role does it have? Funny thing is, it's a completely useless question, and I can talk more about that if you want. But like, not a lot of people really address this when they get to unsolvability quintic whatnot. Like, nobody cares about the answer to this question. But the reason it has the place in history it does is because it caused the invention of groups, and then groups are an unbelievably important thing in modern math, and also in physics and computer science. Like the discovery of quarks was made as an observation about group theory more so than it was made as like before it was an experimentally verified fact. And so you trace back and say, okay, why did they come to exist? And so what I thought it might be fun to talk about today isn't actually the unsolvability of quintic per se, but it's more the blueprints for it and everything that led up and kind of what were the questions being asked. Because it was a little bit mind blowing for me to know the questions being asked by, in particular, Lagrange, who predated Galois, but Galois read a lot of Lagrange's work. It's likely he probably read this one particular one that we'll be talking about. And Lagrange basically just sets the stage for group theory to exist. He doesn't quite invent it, but he asks a certain right set of questions. And when I saw this, I was a little bit mind blown. I'm like, now I understand why Galois kind of came up with the ideas that he did that otherwise felt really out of the blue. And they weren't understood in his time either, right? It's one of these things where Galois was really trying to get other people to appreciate this thing that he was doing. The other people, some of the work they appreciated and it was published. Some of it completely baffled them. Very famously, he before he dies in a duel, he writes up some of his ideas and sends them off. But those ideas that were sent off just weren't picked up for like 15 years. And then even when they were there, it took another 15 years before anyone put it in modern textbooks and things. And a lot of it is that math just wasn't really ready for the ideas, and in particular, recognizing the significance of a group. Um, And so trying to say, okay, what is it that uh, he was thinking about? I think, it does not explain why they're useful, but it does explain why, in the service of solving this one very specific problem, the kind of ideas he came to aren't completely out of left field.
Mm,
Um,
mm.
so we
Yeah,
can dive into the whiteboard
sure.
if you
Yeah,
want.
maybe.
And
Yeah,
some
let's start doing that. So let me try to write what I'm gonna guess might be a rough outline, and you could maybe correct that, just so we have
Okay,
something to
yeah, yeah,
start
yeah.
the discussion. So we're gonna talk about the unsolvability of the quintic. And maybe just to make sure we're all on the same page, right? So a general quintic polynomial looks like I don't know, something like this, right? It has all the powers between 0 and 5, and you want to understand the roots of this degree 5 polynomial, also known as a quintic. And of course, people have studied the degree 2 polynomial in high school, right? You have the quadratic formula. So this is degree 5 because the highest power that occurs is 5. For degree 2, right? We know from the quadratic formula from high school that allows us to write the roots, the solutions of the polynomial in terms of the coefficients, right? And maybe we'll write that quickly later to remind viewers what that formula looks like. But I think my guess is that maybe what's going to happen is we'll quickly maybe talk about the quadratic formula, and then the next difficult problem would of course be degrees 3 and 4, right? So then there's going to be sort of the cubic case. So degree, degree, I'll call D my degree. And then the quartic. Now, these actually do have solutions, although they're going to, as you can imagine, they're going to be quite complicated. And then 5 is really where things get, well, very hard, and that's where we need all the fancy machinery, essentially, to solve it. And I guess kind of along the way, is this, how do you say, is the I mean, I guess, of course, the history of how these problems were solved were by degree, because you have to solve the easier problems before you solve the harder problems. Is the history going to kind of line up in this sort of degree by degree way, or is it a little more
Yeah,
complicated?
yeah, kind of. So the history of it, I guess, you
Yeah.
sort of got around 1500 or so. Leading up to that, the only ones that people could do would be degree two. And it's important to know they were not phrasing things algebraically the way that you and I do. Like this idea of writing something as like x squared plus, um, ax or something like that. You wouldn't see it written in that way. It's a lot more things being described either with the geometry that they're relevant to, which is part of why you only really think of quadratics in the first place, because and maybe like cubics and things, but you're thinking of it as an actual area of something, and then cubics an actual
Mm.
volume of something. And then also it's often described in prose and words. So if you want to say like, when did the quadratic formula exist? Well, it depends on what you mean by exist. Written as a formula, you have some Arabic mathematicians that had started to write something resembling what you and I would have with like square root symbols and whatnot. But in terms of a procedure that could solve problems that are effectively quadratic equations, the Babylonians had a method of saying, if you give me two numbers, there are two mystery numbers and you want to know their sum and you want to know their product, can you deduce what those two numbers are? Anyone who's taken a high school algebra class knows that's secretly a quadratic equation, but they had a method for solving that, which means effectively they had a method for solving quadratics. But however you want to phrase it, up till there, the equals to 1500, very
Wait,
fun
wait.
events happen.
When was that Babylonian
Oh God,
solution,
I will not. It's
roughly?
going to be in the like mini millennia BC.
Okay,
So
ancient,
I'm
ancient.
very
Yeah,
ancient. Yeah, yeah.
yeah.
There's these tablets, and it's very fun actually. It's actually a more intuitive way to understand quadratics. I might talk about this in a moment. Like the way they think about it is a more
Mm,
intuitive way, because it's this puzzle. You're like, I have two numbers. I know their product. I know their sum. How do I
mm,
figure them out? And like that's a very fun kind of puzzle, and it's not framed
mm.
as uh, given this equation, try to find a value that you plug into the equation to make it zero.
By the way,
Um,
do you know who Po Shen Lo is?
yeah, yeah.
Yeah, yeah. I didn't. I vaguely recall he kind of had some like new way of thinking about solving quadratics. I mean, new in quotation marks. I think it was
Yeah.
maybe not standard, but I think he did some research, and maybe this was also the way the Babylonians thought of it, but
Yeah.
it just wasn't.
Yeah, Potion
Felt
loves
better.
it. Yeah, it's kind of just the reframing of how you think about it, and as a pedagogical shift. Yeah, and I can talk about a little what he said.
Sure, sure.
Substantively, it's not different, but it does. Oh, and while we talk about the cubic, actually, it's a little bit relevant.
Okay.
The different way to think about quadratics,
Mhm.
but cubic, pretty much in very quick succession, you have some Italian mathematicians where they were able to solve degree 3, and then like right afterwards, they were able to solve degree 4. And then you have this long span of time until I'm going to maybe say like 1770, where people were trying to figure out, okay, how do you take it one further step? And once you understand like how complicated the degree 4 method was, it seems reasonable to believe that, okay, 5 is there. It's just going to be a real monster.
Mm-hmm.
But then Lagrange basically asked a question that did two things at once. One, it started to raise the possibility that maybe it's not just hard to find, it might actually be impossible, which really shifts how you think about it. Because why would you think it would be impossible? Like, of course, these things have solutions. And we can talk about what we mean by impossible. But then the second thing it did is it suggested that the path to a solution is a more systematic understanding of permutations and of symmetry, which also seems really out of left field. Now, those ideas aren't really taken to full fruition until in 1824. You have Abel, who's a very young, very smart genius from Norway, who kind of takes those ideas and finally proves the unsolvability of the quintic. And more specifically, he's saying there is no expression that I could write that, if we look up and we have all of these coefficients that you always like A5, A4, A3, all of those, there's no expression that you could write that's going to be bringing together those coefficients and systematically giving you a solution all of the time. But that left something to be desired, which was, for example, if you're given a particular equation, something like, x to the fifth minus 2 equals 0, you're like, can I solve that? Can I write down the solution using radicals? You're like, well, of course I can. Kind of by definition, this is the fifth root of 2. And there's also a lot more complicated expressions than that, where you can write down the solutions with radicals. So what Abel was showing was that there's no general solution. There's no formula that we plug in A5, A4, on and on down, and we get out the solution. What he really wanted. Yeah, go on.
Yeah, actually, I realized I maybe I should just be a little more precise, because I did say unsolvability, but I didn't say unsolvability in what sense. So unsolvability in the sense. So what we're looking for. So what's sort of the question, right? Maybe I should have written this earlier, but sort of can you express the roots? So the roots are solutions to this equation being 0, as what's the best way to write it? As a finite, using only finitely many nested radicals. I'm just trying to find the best way to write this.
Well, the way I might phrase it is like, if you're only able to use the operations plus, minus, times, divide, and then nth roots, and you try to just combine those in whatever way you dream up. So that might in particular involve nesting some things. Like when we see the cubic formula, it involves a cube root nested outside of a square root. And the quartic formula involves a square root nested outside of that. But really, it's just use whatever your imagination is to combine all of your symbols using those 4 operations. Can you get this finite expression such that that expression will always equal one of the roots? And, as you referenced, the most famous example here is the quadratic formula, where you take, negative b plus or minus the square root of b squared minus 4ac over 2a, where a, b, and c are the coefficients. And there, it's no matter what the coefficients are, you plug them into that, the thing you get out, it will be a solution. So Abel showed that you can't have that, but there are certain specific ones where you can write down the solutions using just the 4 basic arithmetic operations, nested radicals. He even came up with certain conditions for what properties the equation can satisfy, such that if it satisfies that, you can write down it with radicals. It wasn't a full condition. It only showed like a subset of the ones that would. In today's terminology, the way we would phrase it would be that he showed that if the Galois group of the polynomial is abelian, then you can solve it. And a big part of the why that we use the word abelian in math might actually trace back to this sub-result of his. But then in a little bit later, after Abel actually died, he died when he was 26 of tuberculosis in 1830, or a little before then. There's a lot of work he did that kind of led up to it. But you get Galois, who he basically has his own perspective on the unsolvability of the quintic that goes deeper, and it answers the question of saying, if you give me a particular polynomial, I have this recipe that will tell you, does that polynomial have solutions that can be written with radicals or not? So it's a more refined statement than Abel's, which is just about a general expression that you can maybe plug coefficients into or not. Now both Galois.
Sorry. So did Abel? Let's see. How explicit was Abel's solution? Could you walk up to him, give him a fifth degree polynomial, and he could, with some effort, tell you, yes, this is has a solution or not?
Odds are, if you give him one of a very specific form, he might be able to tell you that one does have solutions that can be written. But most polynomials, the vast majority of polynomials, they have, for those in the know, they have a Galois group that's S5. Mm-hmm. But for the vast majority of polynomials, if you give it to him, he'd be like, oh, that's not of this very specific form. Even though it includes infinitely many, it's just like a probability zero subspace of the infinitely many polynomials out there. The real big accomplishment of Abel was just showing the unsolvability in the general case with these coefficients, and we call it Abel's theorem as a result. We don't call it Galois' theorem. It's often called the Abel-Ruffini theorem because Ruffini thought he had proved it in 1800, but it was incomplete and also just a mess. It was just like so many more pages than it needed to be and incomprehensible. Abel's thing he published was like 6 pages and nice and compact, and Ruffini's was not only incomplete, but it was just a mess. But the key importance of all of these is that ever since Lagrange, they centered on understanding the relationship between permutations and the ability to solve things in radicals, which seems completely unrelated. And so one of the things I'd like to do is to at least make those seem related. But before we do it, the vast majority of our time, we're just going to be spent understanding polynomials as polynomials, solving them as if we're just a curious high school student who's saying like, hey, can you go beyond the quadratic formula?
Sure. Yeah, I think the various nuances of Lagrange and Abel and Galois will become more apparent once we get to them. So I guess we're gonna get our hands dirty a bit because we've talked a little bit about, we've used the terms Galois theory, blah blah blah, and of course without context that's kind of meaningless for the uninitiated. So let's I guess maybe kind of get concrete and see how the story unfolds.
All right, let's begin. Actually, let's quickly review quadratics because never hurts.
Of course.
And so first of all, in general, if we have, give me any quadratic formula. Go ahead and write down a quadratic equation that you might want to solve with whatever coefficient.
So do you want to stick with the notation where we just use an as the coefficient of x to the n?
Give me numbers. Give me concrete numbers.
Oh, numbers. Oh, okay. So let's
one that we'll solve.
Fine. Let's do. Okay. Let's just do. How about x squared plus 2x plus 3. Here's our polynomial.
Great. I guess first of all, you already had the instinct of saying, I'm just going to make this leading coefficient a 1. And, maybe obvious statement, but if it wasn't a 1, we could divide out by whatever that leading coefficient is. Sure. And when we're setting this equal to 0. And so in general, through everything that we talk about, that leading coefficient is just going to be 1. Now, a way to think about this is if you already know that there's 2 different solutions that exist, 2 different roots that we'll call R1 and R2, the whole equation up there is sort of a puzzle because if those solutions exist and there's a way to write the same polynomial factored instead, where rather than expressing it as a sum of all of these terms, we express it as a product of these 2 parentheticals, where in this context, it's very clear if I plug in R1 for x, that the whole expression will be 0. And then likewise, if I plug in R2 for x, the whole expression will be 0. Then you say, oh, well, when I expand this out, it looks like, x squared minus R1 plus R2 times x, because, one of them, there's the x times negative R2, the other one, you've got negative R1 times x. And then when you expand it out, the very last term, and everyone knows this, but it doesn't hurt to just write it out explicitly. If we knew what the roots were, we would be able to also write things like this, which means we can, if we're trying to solve quadratic polynomials, instead of asking what number x do I plug in that makes this whole expression 0, I can instead say, oh, I need this little system of equations where I'm asking, when is it that I can have the sum of two numbers equal 2, or negative 2 actually, because of the minus sign that's introduced, and have the product of those two numbers equal 3. And the way I like to think about this is you might picture a little number line, and here, this will be 0. If I know that their sum is 2, that's actually telling me that the mean of the two of those is negative 1. So I know that this is kind of the mean of my two numbers. And the two numbers have to be equally spaced around that. So it's going to be that mean plus or minus something. So, if maybe they're just sitting here, there'll be some distance that I add to it, some distance that I subtract to it, and that's going to be my two numbers. Mm-hmm. So I already know that, as I've written it here, let's say I want to write out their product. If I write my two numbers as the mean plus some mystery distance and the mean minus that mystery distance, I know that product has to equal 3. But this just looks like a difference of squares. And so when I want to solve for that mystery distance, I can think of that d as being the square root of m squared, the mean squared, minus that 3. And so since we know what the mean is in this case, which is negative 1, I know that distance looks like the square root of negative 1 squared, which is just 1, minus 3. So you've actually given me one that's going to have imaginary solutions, because this will be the square root of negative 2.
I should say we are sweeping some historical details under the rug here, because complex numbers weren't always around. I guess they must have arisen in this context of trying to solve polynomial equations, which is when you would start taking square roots of negative numbers, right?
It is, but not with quadratics, which is interesting. Because with quadratics, if we run into a situation like this where we say, oh, the solution that I want to write should look like, sorry, I keep trying to scroll, and that's why I'm drawing random lines here. The solution we want to write is going to look like, no, I've been writing it as R. My root is going to be the mean of the two plus or minus this distance, which we said is square root of negative 2. If you run into that and you're solving some actual problem, and this is prior to 1500, you'd be like, oh, the solutions don't exist. There just is no value of x that you plug in that makes this expression equal 0, because that requires taking square root of negative. It's nonsense. The only time that people had to take it seriously, they weren't just curious and what if we made shit up, and what if we made stuff up, and I don't know the PG ratings of your podcast.
That's okay.
They were forced into it by what happens with the cubic, which will.
Okay, I didn't know that actually. I don't recall the exact historical development of imaginary numbers, but it's funny because the way I would think of it, but of course this is probably also very anachronistic because people didn't start graphing things until I guess Descartes. But
no,
right?
Exactly,
right?
Yeah.
Because another way you can think of this, this quadratic, which if you were to plot, right, which you were to plot, let me use green, I don't know, right? It would just it's going to look something like this because it intersects this thing at 3, but it just simply doesn't touch the x-axis. That's graphically what's going on. And you could also say that's why it doesn't have any roots. Of course, that's also very anachronistic, but that's another way of thinking about it.
Yeah, absolutely. And I guess one relevant thing that I'll just highlight here, because it's a little bit relevant for how I want to think about the cubic, is how, again, I just really want to highlight how you already know a kind of symmetry of your expression around this this mean of the roots. And so just by looking at the coefficients, we can already tell that the mean of our roots is negative 1. And so there's this kind of symmetry around that. And that ends up being relevant with how you solve cubic equations. Because when we do those, one way that if you tried to map that idea that we just did out a moment ago, you might say, okay, so if I were safe in assuming that it had 3 solutions already, which is already extremely anachronistic because there's plenty of cubics that only have one real solution. And so you wouldn't even be assuming that they have three. But, if we wanted to extend what we just did to say, is there something akin to imagining the system of equations where you know the mean and you know the product? When you expand this out, what you would find is that the initial coefficient looks like R1 plus R2 plus R3 times x squared. And that's because, I might take x times the negative R3, or I might take negative R1 times x, or I might take x and then negative R2 and then x. All of the things that involve two x's will involve just a single one of the roots, and it always shows up negative. Then all of the expressions that might have just one x are going to involve a pair of those roots. So I end up adding together all of the pairwise products, and it's a very nice and symmetric expression, times x. And then at the very end, I'm subtracting off the product of those three, R2 and R3. So you might say, suppose you come over and you say, hey, I want to solve this cubic equation. You've got certain coefficients. Maybe it's like minus 7x plus 7x squared plus 11x minus like 8 as the constant. And you say, when does this equal 0? Rather than thinking about, what can I plug into this expression that will make this 0? You might say, I have a really interesting system of equations on my hand, which is a puzzle. When can I find three different numbers, or can I find three different numbers, so that the sum of those three different numbers is 7, so that this kind of sum of the pairwise product expression of those three numbers is 11 in this case, and such that the product of those three numbers is 8. So this is not at all how people would have been thinking about it in 1500 for so many reasons. One, they weren't writing out expressions like this. Two, can you assume that there's necessarily these roots? But these different expressions for the coefficients in terms of the roots did come up a little bit later with Francois Viet, and we call them Viet's formulas. And they're going to play a pretty important role for us once we get to Lagrange. So it makes sense to bring them up now.
How do you spell the name? I've never heard of this name. I've heard of Cardano,
Viet.
but
Yeah.
Okay.
So he was a French mathematician. How much after Cardano? At least 100 years, maybe a little bit more.
Okay.
He was the one that really started introducing algebraic notation as we know it today. And he was kind of the father of algebra in the sense of the symbolic manipulations that we do. Thinking of things through this lens, I think, can be a little bit clarifying for imagining polynomials. In particular, again, I just want to draw attention to the fact that the coefficient in front of the x squared term, the one that's kind of right after, this tells us what the mean of all of our roots is going to be. We know that a third of that value, if you kind of multiply it by a third, that tells you like where the mean of the roots is. So if you were picturing this polynomial in your head, and I actually know what the polynomial is, so I'll draw it like this. Those three roots, which at the moment are a mystery, you can know right away that the mean of all of them sits at negative 7/3, or 7/3, sorry. So you multiply by, and in this case, by the way, that you could actually solve this system of equations just by guessing and checking. The roots turn out to be 1, 2, and 4. So you might wonder, like, oh, is there some way I can always do this without guessing and checking? And the first step, and the reason I'm making all of a hubbub about this leading coefficient here, is that we want to get rid of it. We want to basically have a cubic to deal with where there is no x squared term.
Actually, let me pause for a second, because you said you can kind of guess and check, but I think, how would I say? You could, it seems like you could reduce it to the quadratic equation, because once you know the mean, right, then you only have 2 degrees of freedom left, and then, right? Is that right? I mean, yeah.
That's actually a really intriguing statement right there, which is the heart of where we want to get to. You're like, once you know the mean, that gives you 1 degree of freedom that we've locked down. You're left with these 2, and so that those 2 remaining, they feel like a quadratic.
Right.
They're not quite, though, right? Because this system of equations here, where you have the sum of the pairwise products, and then you also have the product of all 3, that is a different kind of thing than the system of equations that a quadratic equation asks,
I
which is
see.
when you, I won't use R, but maybe I'll use like S or something. If you know the sum of two different things
Yeah,
and you know
yeah.
the product of those two things. So you're 100% right. Some kind of reduction can take place. You're also 100% right, actually, that we can do that, make that reduction look like a quadratic expression. However, it's not obvious how to do it. How do you
Yeah.
reduce a
The,
cubic
the
into
problem,
a
yeah, okay, yeah.
quadratic?
The problem is that uh, I say reducing degrees of freedom is orthogonal to the degree in the algebraic sense of the problem. So the problem is that this last one right here, right, has degree 3 in the roots, and that's not going to disappear even if you reduce the
Yeah.
degrees of freedom, right?
Um,
Yeah, yeah,
so for people with like linear algebra based intuitions, when you're dealing with linear equations, like the instinct that once one degree has been eliminated, 1 degree of freedom is down, the whole system of equations is reduced in degree, and that those
right,
are all kind of the same sort of thing. Like
right.
1 degree
Because
two
it's
system is
linear,
the same
right?
as another because it's all
Exactly.
linear.
That's right.
Here we're dealing with very messy, like highly nonlinear things. You've got like
Right,
all these.
right.
Oh,
Okay.
didn't mean to erase that.
Yeah.
All these nonlinear relationships between the
Yeah.
roots. So it is a
Mhm.
system of equations. We are removing one of the dimensions of it. So it is a lower dimensional system of equations.
Right.
But whether that's like isomorphic in some sense to the other kind of lower
Right.
dimensional nonlinear system, which is solving a quadratic, it turns out to be true. It's just not obvious that it would
Okay.
be.
Okay.
Um,
Okay. Yep.
so step one in this elimination, basically what I'm going to do is I'm going to change my coordinate system. So what I want to be the case is that that x squared coefficient is 0. Another way to say that is that I want the mean of my roots to be 0. And I already
Right.
know what the mean is. So I'm basically going to say I want some system, I'll call it like x prime instead of x,
Mm-hmm.
where the line where x prime equals 0 should be right over that mean.
Mm-hmm.
Whereas, uh, the line for x equals 0, the usual y-axis would be over there.
Mm-hmm.
And so if you do the substitution where we just plug in um, x prime,
I
how
guess
do I want
equals
to phrase it?
x plus 7/3, I guess.
Yes, that would be it. But let's write it the other way, actually. We'll write it as x equals x prime minus 7/3,
Okay. Yep.
which more generally would be x prime minus, I'll call that like b, whatever that coefficient was, thirds. If you just plug this into your equation, I don't think you and I want to do it now, but viewers at home who love
Mm-hmm.
doing algebra can try it out. If you just plug this into your equation, what you'll get out is a cubic polynomial in terms of x cubed, or x prime cubed, maybe I should say. So you get something that looks like x prime cubed. Magically, the quadratic coefficient will have gone to 0. So it'll be x prime squared. And then you'll end up with something else that it's not going to be 11 and 8, but we'll call it like p times x prime plus q. Uh, and solving for your original equation will then become equivalent to solving this new one for x prime, where you have no quadratic coefficient, but you do have a linear and a constant coefficient. And then after you find that solution, all you have to do is shift back because it's basically just a change of coordinates we've shifted.
Mm-hmm.
So this whole process is called depressing the cubic, where the first thing you do is you shift your coordinate system so that it'll have 0 as your new uh, quadratic coefficient, solve that, and then shift it back. All of this is a very long-winded way of saying if you're given this simpler form of cubic equation, or if you're able to solve the simpler form where there's
Mm-hmm.
no quadratic coefficient, it's not a loss at all. There is no loss in
Right.
generality because you can always depress it. Also, little side note, what if you depress a quadratic? What if you're given a quadratic and you say, oh, I want to shift my coordinate system so that the sum of the roots is 0, and then I'll shift it back? That just is the quadratic formula.
Mm-hmm.
Like it pops out immediately because once you have an
Yeah.
expression that just looks like x squared and there's no other term, and
Mm-hmm.
then it's c equals 0, you just take a square root and then you shift it back,
Mm-hmm.
and that's all the quadratic formula is like shifting things.
Mm-hmm. By the way, yeah.
um,
So I mentioned Po-Shen earlier. I mean, these are all the same ideas, I think, right?
yeah
Yeah.
yeah
Okay. Yeah.
That's why
Yeah.
this is like sort of
Yeah.
two different ways of thinking of the quadratic formula. One of them is that you depress it, you shift your coordinate system, you do a substitution for, in this case, negative b halves,
Mm-hmm.
see the new thing that comes out, take a square root, and then shift it back.
Mm-hmm.
The other one can be thinking of the mean and the product of the roots. And I often just like think in my own head, like a simplified quadratic formula um, is, I'm sort of writing all over the place here, but uh, the mean plus or minus the square root of m squared minus p. Like that's the thing I have memorized,
I
where if I
see.
know the mean of two numbers and I know the product of the two numbers, I just plug it into that, which
Got
is,
it.
it's more compact than the quadratic formula.
Mm.
Um,
Hmm.
I don't want to like rederive it on the fly every time I'm going. So the
Sure.
Cauchy-Low method, it's great, right?
Yeah, sure.
If you're like teaching and you want to understand where it comes from.
Hmm.
But the reason I bring that up, actually, in a moment, we're gonna use this. We're gonna have a situation where we know the mean of two numbers or the
Mm.
sum, and we know their product, and we just want to like plug that in.
Hmm.
But in our case, it'll be solving the cubic.
By the way, do you know why it's called depressed? It's such an emotionally charged word in the modern word. I guess depressed means you're like eliminating the square, I guess, right?
Yeah, yeah,
Yeah,
we're
okay.
taking that quadratic coefficient. We're just like moving
Yeah.
it down to zero. Where
Yeah,
it was
okay.
a non-zero value, and we've
Yeah.
pushed it down to be zero.
Okay, yeah.
So
Yeah. I guess it's like maybe that would in modern like I think if I were to be a like linguist, maybe that's like suppression, not deep like depression just sounds too emotional. But I'm being a little fruity, but I I'm just like if I were writing like in terms of the English language, I think suppress might be a better word than depress, but maybe I'm just being silly.
maybe,
Maybe I'm just
yeah.
being like a marketing like I wouldn't want to if I'm like a math you know YouTuber, right? I wouldn't like want to use the word depression in my math videos. Maybe.
I like evocative terminology. I
Oh,
mean,
okay.
in this case, maybe it's a little, uh, used incorrectly runs the risk of being insensitive because, you have other crazy terminology like monster group or things that
Mm.
it's like hilarious and wild, but that makes it more fun.
Yeah, yeah, yeah.
I don't know. It's evocative. We've got this cubic. You want to first have to
Depress it.
make it
Okay.
depressed, then it's easier to work with. So, with all that as preamble, let's talk
Okay.
about how do you solve a depressed cubic?
Yes, let's
So,
do that. Okay.
you come and you give me and what do you prefer? Do you want to do this with numbers on a specific example, or do you want to do it with algebraic symbols to like let the general formula pop out?
I think I'm fine doing it with general symbols because
So,
yeah. I mean,
so
are you happy with that too?
yeah, it
Yeah.
just
Okay.
kind of
Oh yeah, let's
kind
do
of
it.
depends. I think
Okay.
it sort of depends on the like age range or maturity of your,
I
like if
see.
I was like doing this as just an exercise with like early high schoolers,
Mm.
um I might just like plug in some numbers where it, because as you'll see, a number of symbols end up popping up where we're like defining
I
some new
see.
thing and
I
whatnot.
see. Although, given
Uh,
I guess maybe my audience might be like my videos have been like on category theory and most recently the standard model. So I think I assume a higher bar.
all of this, yeah, all of this, your viewers are sitting here like, all right, so we went from the standard model to now suddenly going back to high school algebra. I
Yeah,
don't know
yeah,
what we're
yeah,
doing.
yeah,
It's
yeah.
historically interesting. And
Sure.
I'm putting the ideas kind of anachronistically because it's really not, it's actually not that enlightening to see how Cardano and others wrote it down.
Mm,
Because again, it does involve a lot of prose. It's you take these things that are split into like six different cases when they should be one because they're
mm,
afraid of negative numbers.
mm,
Like negative numbers just aren't really a thing to them.
mm.
Um, but I'm trying to write like the meat of what they actually did in
Sure.
modern symbology
Sure.
because the relevant progression of ideas is basically going to be all you need to remember from this is the fact that they were able to reduce a cubic into a quadratic.
Hmm.
And then the next thing that they'll do is they'll reduce quartics into cubics. And that kind of reduction suggests a sort of recursive process that you
Hmm.
can do to solve any polynomial. And
Hmm.
understanding why that breaks will be interesting.
Yeah.
Um, so when you look up the cubic formula, and it's
Hmm.
called Cardano's formula, which we'll write down in a moment, um, it is a bit of a mess. It's a large thing. You are not going to, unless you love memorizing things, you're not going to remember it after you first see it. But the only thing you need to remember, if you're launched back in time and you're suddenly challenged to some sort of math duel where people are asking you to solve cubic equations, which sounds like a joke, but that's actually how these things were discovered.
You know why
Have
when
you-
you said that it made me think like those like r- rap duels where you freestyle and you call each other out like there could be a math version of that maybe where you
well,
might need this skill.
I mean, maybe you've heard it, but let me tell you the story behind this before we dive into it, actually, because it is great. Like, this was in a culture in Renaissance Italy when this was how mathematicians made their way. It wasn't by having publications, it was by having these public math debates, or we're just going to call them math duels because that sounds more fun, where you would challenge someone else who had like a good reputation. You would give each other a set of problems. Whoever solved more of the other person's problems would win this math challenge, And it would have material consequences sometimes. It might be that the actual stakes of it were, a feast for the other person. You might implicitly get some patronage based on the attention that you raised while doing that. And so what happened is that a one particular mathematician, I might get the names a little bit mixed up, but I believe he was Del Ferro, figured out a way to solve cubics, or at least a subset of them, but kept it secret so that he could win these math challenges. Before he died, he passed it along to his student, I think Fiore, and Fiore was a little bit less scrupulous with it and then just goes and starts challenging everyone to math duels. And so people look, they're like, okay, something's going on because this kid wasn't that bright before, and now he's suddenly beating us at all of these questions, which could be boiled down to cubic equations, but they would write them in prose and such. And so another one, Tartaglia, or Tartaglia wasn't his actual name, but it's a nickname based on the word stutterer because he had gotten an injury when he was younger, which is a bit sad. He says, okay, if this kid can come up with a cubic formula, surely I can come up with a cubic formula. So he discovers his own, again, keeps it secret, and starts like winning these math duels as a result. But we don't call it Del Ferro's formula, and we don't call it Tartaglia's formula. We call it Cardano's formula. Cardano was a medical doctor, actually. He wasn't even a mathematician. He was a polymath. He liked all sorts of things. And so he wanted to understand mathematics better. He saw that Tartaglia clearly had a solution. Basically, Cardano comes up to Tartaglia, says, bro, we know you have a cubic. Let me know what the cubic formula is. And Tartaglia says, no, couldn't do it. Very valuable. And Cardano says, come on, I'll be cool. Like, maybe I introduce you to some patrons. Just let me know what it is. And Tartaglia says, all right. I'll let you know, but you have to swear a solemn oath to God that you won't tell anyone else, and you'll let me publish it before others. And Cardano was like, for sure, I'll do that. So Tartaglia tells him, and he does so in a poem, which is funny. So you can look up this like poem in prose that is the cubic formula written out in verse. And Cardano's like, great, love it. He develops it further with his student, whose name is Ferrari. Cardano and Ferrari take it further. One, they make it more general. They understand this process of depressing the cubic and things like that. Two, they discover a quartic formula. But critically, the way to solve a degree 4 equation involves a first step where you reduce it to degree 3, which we'll talk about. And then you're like, oh, but we know how to solve degree 3. So Cardano really wanted to publish this. He's like, wow, we found this new thing, but part of the process is the ability to solve cubic equations. I promised Tartaglia that I wouldn't publish about cubic equations before he did. My hands are tied, oath to God. But then he's a curious man. He's snuffling around. He finds the notes of Del Ferro, the actual original person who found it, realizes that Del Ferro found this formula and thinks, oh, I'm not publishing Tartaglia's. No oath broken to him. I'm publishing Del Ferro's results. So he like publishes this book. I actually have a translation of it sitting on my thing here,
Wow.
Ars Magna.
That's amazing.
And then Tartaglia is just infuriated and has this like lifelong vendetta against him for breaking this oath. And there is one, and so he like tells the story of it in here, which is very funny for anyone who's like curious, and this is where we get it. But there's also one little quote from here that I kind of want to, I should have underlined it, because the way that he describes cubics, just to give you a sense of how these people were thinking about, like, to you and me, it's like, okay, this is a mild curiosity associated with solving certain equations. Like, I guess there's some formula for it. What's the big deal? The standard model and things like that are going to be more fun. But the way he writes about the ability to solve cubic equations, this is how he writes it in like the first publication that reveals cubic formula ever. He says, since this art surpasses all human subtlety and the perspicuity of mortal talent, and is truly a celestial gift, and a very clear test of the capacity of a man's mind, whoever applies himself to it will believe that there is nothing that he cannot understand. So they took this stuff seriously.
Yeah.
They really cared.
Wow.
But it's something you and I can rederive because of like modern notation and a little bit of savvy well, you'll see, we can rederive it in like 5 minutes. So
wow. Thanks for that digression. It's great.
The only thing you need to remember, if you're thrust back in time, you're thrust into one of these math tools, the only thing you need to remember is that Cardano's formula looks like something plus something. If that's all you remember, you're in good hands to rederive everything, which seems like it's completely substanceless, but it I don't know if it motivates, but at the very least helps you remember the first key step, which is to say, I'm going to assume that my solution looks like the sum of two things. We'll call them W and Z.
Mm-hmm.
And I'd say, how is that possibly helpful? Like, just walk with me here. One of the things we notice is X shows up cubed in our equation. So it might be helpful if we're going to write it as the sum of two things to understand what that sum looks like when we cube it. You say, okay, what is the cube of an expression like this? And this is nice binomial formula stuff. This will look like W cubed plus 3 times W squared Z plus 3 times W times Z squared plus Z cubed. And I'm going to simplify this a little bit further. I'm going to call this W cubed plus Z cubed. Just want to think of this kind of sum of the two terms cubed sitting on their own. And the reason I want to do that is that in the rest of the expression, this middle part, there's some shared terms, like they both have a coefficient of 3. They both have at least one W and at least one Z. So I can do a little bit of factoring and write this as 3 times W times Z, all outside of W plus Z. And you might say, okay, you've just expanded a binomial expression. How does that help me to solve any kind of actual equations? And I would invite you to notice how this expression here, the sum of those two, that's just an X. And on this other side here, we were looking at an X cubed. Mm-hmm. So if I rearrange a little bit, and if let's see, can I copy? I'll just write it out again. If I write this whole thing as W plus Z cubed, thinking of that as analogous to the X cubed up there, and then I subtract off 3WZ times W plus Z, which I'm thinking of as analogous to my P times X, because we've got an X term sitting in here. Then I've also subtracted off W cubed plus Z cubed. This equation here is a thing that is true for any W and Z. This is not at all tied to our original polynomial. This is just a fact. If you give me two numbers, this equation is true of those two facts. It just follows right out of expanding all of that. But because it has a form that looks so very similar to the original depressed cubic that we have above, I can basically say, if I were able to find, if I were able to find a specific pair of numbers, W and Z, so that these coefficients lined up, which is basically saying I want P to be the same as negative 3WZ, and I want Q to be the same as negative W cubed plus Z cubed. So I remember P and Q are just numbers. Those are the things that we know already. If I can find a pair of numbers, W and Z, that satisfy these two equations, then I've solved what I need to, because X is just the sum of those.
Right.
I remember earlier you're like, we've reduced it to a pair of equations instead of just one, but it wasn't quite a quadratic. Now, this system of equations we've reduced it to is basically the same as a quadratic system. It's a little bit different, but we might think of saying, okay, we know the sum of two numbers. Specifically, we know the sum of W cubed and Z cubed. So I write it as, W cubed plus Z cubed is equal to negative Q. And I also know the product of those two numbers. I know the product of W cubed and Z cubed, which looks like negative P over 3. And so now you can think of this as a quadratic if you want to.
I guess you need to take the cube of the right-hand side?
Yeah. Oh, yes. Yeah. So that's P cubed, and that's 27. So if you wanted, you could say that these intermediate values, my W cubed and Z cubed, are solutions to what you would call a resolvent equation. And so that resolvent would look like y squared, where, okay, the sum of those looks like negative cubed. So negative Q, so I'll write it as plus Q times y. And then the product looks like negative P over 27.
These are exactly the same mean and product equations we saw earlier, and you're just writing the quadratic that goes along with that.
Yeah. So when we're saying we reduced the cubic to a quadratic, this is the specific quadratic that we've reduced it to. And so if we want to say, what are these two values, using the whole like mean product formula or the quadratic formula, whatever your favorite method of solving this kind of system, this kind of setup is, it's going to look like the mean, which is negative q over 2, plus or minus the square root of that mean squared, q squared over 4, minus the product, which in this case looks like plus p cubed over 27. So that tells us what w cubed and z cubed both are.
Yeah, but let's pause for a second. Um, this strikes to me as something that's like, oh, you look up some solution at the end of a contest problem solution. Like, where did this come out from, right? So it's clever. But it's like, where, where did it come out from?
Yeah, absolutely. So I've tried to motivate it as well as I possibly can, which relies on one leap of faith, which is to remember that the final answer looks like something plus something. I'm dumb, so I can remember that. So I can come into a talk like this, not having memorized the cubic formula, but confident that we can rederive it. Why would you think to do that? Why would you think to say, like, what if I can express my solution as w plus z? What if I expanded out the cube of that? Because the only motivation I gave there was saying, well, a cube shows up in our expression, so maybe we just want to have on hand what it looks like when we take this proposed formula that's something plus something and we cube it. And then after you cube it, you have this pattern recognition kick in where you're like, oh, interesting. Once I cube it, I have my w plus z cubed, and I also have a certain thing times the w plus z, but there's no square term for it. And so all the like coefficients line up. Where does that come from? That's kind of the question that Lagrange ends up asking in 1770. Because if you think this method is arbitrary seeming, you should see the quartic method that they came up with, where again, it's like you do this judicious substitution, you do this certain manipulation, it works, you're able to reduce it. And the way they did it, I think, is just to try a bunch. They just tried a whole bunch of different things, and some of them hit and some of them didn't. And Lagrange wanted to have a systematic understanding of how would you find that in the first place? And in particular, could you use that systematic understanding to then generalize it and go beyond just 3 and beyond just 4 and get to 5?
Mm-hmm. Mm-hmm.
And so anyone who wants to kind of fill in the details here, you can basically see what each of these somethings are. They'll be cube roots of the two possibilities for this expression, which it's not a huge formula, but it's quite a bit to manage if you take the cube roots of those and you add them together. But if you ever look up Cardano's formula, the one thing that's actually worth remembering, not that none of it's worth remembering, it's a useless formula. It's not totally useless, but like no one's using this in practice. It's better to just do a numerical solution like Newton's method if you need to solve some cubic out there. Like the formula is a bit of a mess. But the relevant thing is that sitting inside Cardano's formula is a little quadratic formula, something that's more familiar. And that is a residue of the fact that the method involves this reduction to a degree 2 equation. And so, like I said, later on, Cardano and his student figured out if you're given an arbitrary degree 4 equation, so x fourth plus, a whole bunch of things equaling 0, they had an even more elaborate system of things that they could do that resulted in what we might call a resolvent cubic equation, something that is another cubic equation, so that the solutions of that smaller cubic could be used as intermediate steps in the solution of your quartic. Now, I could never remember the thing that they did. But if I was left on a desert island and someone said, here's this degree 4, polynomial, or can you come up with a general formula for degree 4 polynomials? While I have no idea what the Italians did, read it once, completely forgot it, the way that I would rederive it would be to come at it with the Lagrange approach, which we will now start talking about. And it takes a little bit of motivation, but it's not too much to get there.
Maybe let's just pause really quick. So I think one thing that's maybe easy to overlook here is the fact that it's not clear from this way of writing the solution. So I'll just circle it. So here, why there are exactly 3 solutions, right? Because right?
Great question.
Right? Because you have 2 from the plus or minus, but then a priori you're going to have 3 times 2 when you take the cube root, because when you take a cube root, there are 3 possible roots in the complex plane, and then a priori that multiplies with the 2 that you have under the square root. So why are there only 3 distinct roots?
Excellent question. Okay, so first of all, this w cubed and z cubed, keep in mind they're different, two different numbers. They're assumed to be like, oh, we're writing x as w plus z
Hmm.
cubed. So it's not actually the case that we have two different, like this plus and minus is a little bit misleading, where when you write it out in Cardona's formula, one of the I'll just write it out actually
Hmm.
on the left here, instead of writing it as something plus something. Um, we have to use both of them. And initially, it kind of looks like Cardona's formula is only showing one solution and not the other three. Okay, so the first thing we put in is a giant old cube root of, and then I'll just write it out. Why not? Negative q halves plus or minus square root q squared over 4 plus p cubed over 27. And then the next thing is cube root, and then the other one, q halves. Sorry. The whole point of me writing this, and I didn't even, on one of them you do plus, and
Mm.
then on the other one you do minus. You can't
Mm.
do like plus for both of them or minus for both of them. That would be invalid. Um, so this only gives you one solution actually. And the uh, the original way that they would have thought about it, this gives you one real number solution. And then if you want from that, you can, I
Actually,
don't think,
let's go back. Sorry. Where in the derivation did we? Sorry. Oh, right. Because W. Right. The W and Z are the distinct roots. Okay, so that's why you take different one. That makes sense, right? And then the question becomes what those cube roots mean, right?
yeah.
Yeah.
So uh, quicker answer to your question.
Yeah.
If we take a cube root, you can take like just the positive, the one with the highest positive real part, and call that like your first cube root out of the three available. If you were thinking of this in the complex plane, of course they weren't thinking of this in the complex plane.
Mm-hmm.
They didn't have complex numbers, anything like that. But
Let's see.
you and me
Yeah, I guess
looking
the
at it
first.
today.
I see the first. I see the. Oh, right, because a cube root always exists for a. Oh, actually, wait. I'm trying to think. The inner square root is always positive. Oh, but the cube root could be either positive or negative. But fine, because you always take the real. Take the real cube root, right?
Yeah, and sorry,
Yeah.
for a real, if it's a real number input also,
Yeah.
then you always have one cube root.
Yeah.
It's
Yeah.
just, what's the
That's
cube
right.
root of 8? It's 2. What's the cube root
That's
of
right.
-8? It's -2.
That's right.
So no ambiguity if you just want to deal with real numbers.
That's right.
If you were lucky enough that the stuff that came out on the inside was a real number,
Mm-hmm.
then no ambiguity, and this just gives you one solution. As it happens, if you want the other two solutions, then let's let, I'll do this in a different color. Let's let omega be a cube root of unity. So e to the 2 pi I over 3. You could get another solution by taking omega times this first one and then omega squared times the second one and adding those together. Or you could get the third root by swapping those and instead taking omega squared times the first one and then omega times the second.
Is it obvious that you had to do that prescription?
No, it's not. But the one constraint that will maybe kind of make it obvious is the fact that you need the product of your three distinct roots to be a real number. And so if you just take those cube roots as multi-valued functions initially, and you say, this top cube root, strictly speaking, has, three different solutions in the complex plane, and this other cube root has three different solutions in the complex plane, then there should be like 9 combinations of those. And you might wonder which of those 9 combinations is an actual solution to my original equation. Not all 9 of them can be, but the relevant constraint is that their product does need to be Q. And do we need to use the other constraint actually on the other product being on the, not the product, but the sum of the pairwise products
Sorry,
being real?
wait. Let's see. Sorry. There's the equation for the cubic in terms of x, but if we're working with w and z still, the constraint on the product is coming from this p equation, right? So
Oh, sorry. What I mean is like if if you want to have three distinct solutions that all have this form, so once you've gone through
Oh,
your
I see. Yeah,
WZ
yeah.
stuff
Uh-huh.
and you've
Yeah, yeah,
come
yeah.
back and you say, okay, I have this expression.
Oh, right, right,
Um,
right.
and it's not a given that that would give you all of the solutions because you just sort of posited like, what if I express X as W as a sum of two things?
Hmm.
And then what can I say of those two things? And you kind of get these expressions for it. Um, but let's see. So
I think seems to me that the logic should be that every possible cube root is a root, but but there's redundancy because I don't see any like how do I say? You've expressed sufficient conditions for things to be a root. What's what's I guess maybe not clear is why there are redundancies, right?
I, you
I
know,
think that's the logic. I might
I
be
think I
wrong.
was a little bit hasty a moment ago when um, you were pointing out how the relevant product. If we look to the expression for P and Q down here, I think this actually tells us something. Where when you if we're saying what can W and Z be that satisfy these two different equations,
Hmm.
um, for example, it has to be the case that when you uh, take the product of W and Z, that you get out a real number, and that okay, that definitely does constrain you all the way, actually,
Mm.
because if we just take this first one, the first term, you say there's three interpretations for that cube root. Either it's the real value times omega, the cube root of unity, or it's the real value times omega squared. Whichever one of those you choose, it locks you into what the other choice has to be. Because if you know what W is, it locks you into what Z has to be.
Mm.
Um,
Oh,
and the
I see.
fact that we were dealing with cubes, because we took this equation of P equals negative 3 times WZ and we
Yeah, yeah,
cubed
I
it,
see.
but that effectively crosses over a lot of potential values where
That's right. That's
when
right.
we're taking the cube root of that to kind of go back.
Yeah,
Uh,
because when you cube an equation, you're introducing more roots than the original equation, right? So this
yeah,
was, yeah, okay. Okay. I think that's the solution. So this is the original one where uh, solutions to this are solutions to the original one, but we actually cubed it when we go to this guy. And so to go back from the cube solutions to the um, original solutions, that's where the constraints come in. Okay, I think I'm
yeah,
happy now. I'm happy.
yeah.
Okay,
Um,
great.
but yeah, so just for all of that, the broad takeaways, I guess. One of the phases reduced it to a degree two. Two, it felt like a lot of random steps that we made in order to do that,
Oh yeah.
right? Um, so uh, let me, because we've gone on a little bit while, let me tell you the outline of Lagrange's insight before I explain why it's true. So this thing that we just did, I'll just kind of write it out schematically, where we had um, a cubic equation was zero, and then we reduced it. I'll stay in the same color. We reduced it to a quadratic equation so that the solutions of that quadratic help you with the cubic. And then later on, they went even further and said, if I have a quartic, I can reduce that to some other cubic such that the solutions of that cubic are intermediate steps on the way to
Hmm.
solving that quartic.
I imagine that's even an even more clever substitution and
It's
manipulation.
wild. But
Okay.
I can show you how you can rederive it, and it'll be very fun. Because what Lagrange basically did is he found an association between these kinds of reductions and what I'm going to call almost symmetric expressions.
Hmm.
So, uh, one example of an almost symmetric expression would be a squared b plus b squared c plus c squared a. This is going to feel like a completely unmotivated, out of left field thing for me to even be saying, but no, not equal zero. No, no. This isn't even. It's not an equation. This is just like an expression sitting out in the wild that just wants to be an algebraic expression.
Hmm.
Um, this, it's when I say almost symmetric, I mean if I take the symbols and I swap them. Uh, so I kind of maybe I replace A with B, I replace B with C, and I replace C with A. I'd actually get the same expression.
Hmm.
It would look different, but it would be algebraically identical. However, not all permutations keep it the same.
Hmm.
For example, if I just swapped A and B and I left C fixed, um, I would end up with an algebraically distinct expression. And in that case, we can go through it. What would I get if everywhere where I see an A, I write a B. Everywhere I see a B, I write an A. This would look like B squared A. This would look like A squared C, and this would look like C squared B. And so these are two distinct
Or I think
expressions.
you mean a squared b. Yeah, your
Uh,
c squared should become a squared. Or oh, sorry, you're only switching
the
a and b, right?
Yeah,
Yeah.
because
Oh,
I
sorry. Yeah. Sorry, my bad. My
exactly.
bad.
I'm
Yeah, yeah,
deliberately leaving C static.
yeah. Mm-hmm. Yep.
And among all of the six different permutations you could apply to A and B, they would necessarily just take on one of these two distinct values.
Mm-hmm.
So I have an expression with three variables, but it takes on two distinct values.
Mm-hmm.
Unexpectedly, Lagrange showed why that is connected to the fact that if I take something which is a degree 3 polynomial, I can reduce it to the task of solving a degree 2 polynomial.
Mm.
Sounds out of left field, but I'll explain why. Similarly, below, I can find an expression that involves four distinct variables, but where as I permute those four variables, the expression as a whole takes on only three distinct values. And so this almost symmetric expression that I've chosen
Mm-hmm.
looks like A plus B times C plus D. You can find others. There's other choices we could make.
Mm-hmm. Mm-hmm.
But some of the permutations I apply, like if I swap A and B or if I swap C and D, doesn't change the expression. But some of the permutations, you might land on something that looks like A plus C times B plus D. That would be different. And you might also land on A plus D times B plus C.
Mm-hmm.
So this is very unusual because most expressions, if you write with four variables, as you go through all 24 permutations of them, they take on 24 distinct values. Some expressions are very symmetric, like the product of those four variables or the sum of those four variables. Those take on only one value. So we're in this kind of intermediate range where expression with four symbols takes on three distinct values. Lagrange basically showed if you show me an expression like that, I can show you a way to reduce any degree 4 polynomial to a degree 3 polynomial. He gave this recipe, and I can talk through it now if you want. And if you and I were on a desert island and we desperately had to solve a degree 4 polynomial, this is how we should do it. Because
No, I
this
like
is a
this. I
lot
like
easier
this.
to
Yeah,
remember.
that it's. I guess it's sort of intuitive because you're basically all all these kinds of tricks ultimately involve some kind of structure in the possible expressions of polynomials, and I guess the key magic is that that structure is actually encapsulated in group theory essentially. I guess
Yeah.
that's the magic that I don't know and would now like to hear.
Yeah. So, and no one in the world knew this. And so, before explaining why this magical connection is true, let's just take a moment to think about the implications. One, the natural next step that Lagrange asked, because no one had been able to solve degree 5 polynomial equations, he said, can you find an expression with 5 distinct variables that takes on 4 values as you permute them? That sounds like just a brain teaser. That sounds like
Mm,
something you could find at the end of a puzzle book. You think about it a little
hmm.
bit. Oh, try to find some. I don't know. Maybe you try
I see.
A plus B plus C all
Hmm.
times D plus E. And you think through, oh, how many distinct values does this take on? And you're like, well, okay, I'm basically going to have 5 choose 3 determines what that first parenthetical is going to look like.
Mm,
Okay, that'll be 10 values. So this takes on more values than it should. I needed to take on only 4. Can you get clever? Can you find
I
some
see.
expression?
I see. So is the statement that basically, uh, this is of course is a counterfactual statement, but okay, but like in degree n, if you can find a polynomial expression such that its orbit under the symmetric group is of size n minus 1, then you could reduce the problem to solving the degree lower polynomial.
Yes.
Okay.
Yes.
Okay.
That is the perfect way to phrase it.
I see.
And Lagrange said, I don't know. But he speculated it might be impossible because he tried hard and he couldn't find one. And he also said, we need some kind of, and his use of words was combinational calculus to answer this sort of question. These days, we would call that group theory,
I
but
see.
I like combinational calculus kind of
Nice.
sounds like
So,
a
so,
nice.
so is this really the origin of group theory? Would you
Uh,
say,
in
in
my
some sense?
opinion,
Okay.
I think so. I
It
think
sort of
this
makes
is,
sense.
yeah.
Yeah, because of
Um,
course, it sort of makes sense that like the most natural group in some sense is the permutation group, right? And we already see that that is coming.
Yeah.
up here. Yeah.
Yeah, and for the first many decades of group theory's existence, it was the only kind of group. It was just always thought of in terms of
Hmm.
permutations. The idea of abstracting it in terms of like a set with a certain binary operation, satisfying such and such.
Yeah.
That's a much more modern way of thinking.
Right.
And
That makes
like by the
sense.
time you get to Emmy Noether and Artin, and they're formalizing things the way I like to formalize things,
Yeah.
you'll see it there. But
I'm
in terms
guessing,
of
yeah, I'm guessing what happened is you think everything in terms of the symmetric group, then you start thinking of subsets of them, and then it becomes awkward to tie them to particular subsets of a particular symmetric group. And then you could just say, okay, let's just think about groups abstractly, right? Because you could think of like just the even ones or cyclic subgroups, and then it's kind of always annoying to carry around the explicit coordinates if you want. And then you could just say, okay, it's just some abstract group. I'm gonna guess that's maybe like how I would have like stumbled upon it, maybe.
yeah, but it's just not that much more awkward to think in terms of permutations. And like any group in the abstract definition, any group can be expressed as a permutation group. This is Cayley's theorem.
Right.
I think the motivation is just that proofs become a lot easier if you have clear axioms that you're working with, and you just have to
Right.
make sure things satisfy those axioms.
Hmm.
Then you can prove it. And also, it helps make clear when groups that they don't look like actions at first.
Hmm.
So like the fundamental group on a topological space, or like braid groups would be examples where they don't feel like an action at first. They feel more like a thing that you can do combinations of things
Hmm.
that happen to be associative. Um,
Hmm.
but yeah, certainly in the origins, it's all about permutations. And I mean, you said, is this the origin of group theory? There's a lot of different origins. Like a completely different direction was Gauss studying quadratic forms, and something that had nothing to do with the unsolvability of the quintic, but also involved uh, class group coming up. And it was just from a completely different angle. And really, it's that you have a lot of distinct but similar seeming ideas that converged in the late 1900s, but sorry, late 19th century. But for our purpose, if we're just studying on the unsolvability of the quintic, this really feels like the originating moment. Especially if we're willing to speculate that Galois might have read the relevant paper where this was happening, which we
Mm.
don't know for sure, but
Mm.
we do know he read a lot of Lagrange's work, and like it probably was in the milieu in some way.
Okay.
Um,
Okay. All
so
right.
why the
Yeah.
heck are these
Okay.
things connected?
Yeah. 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 So now I wanna unfurl it. Okay. So where is the group theory gonna come in now?
Yeah. So the group theory will be used to answer this question, to
Hmm.
say, we can pretty quickly answer why you could not ever write an expression with five variables that takes on um, four distinct values. That doesn't prove the unsolvability of the quintic, by the way. It's basically just saying that if you could solve the quintic, you couldn't do it in this way. It
Right.
wouldn't
Right.
be
Right.
something that, in the same way the Italians did it, had this first step of
Right. Right.
reduction and
But I think
whatnot.
that's already quite that's a good start because Galois theory requires much more work. But if the how do you say your um, Lagrange had good sense in that, and I guess a bit of boldness, I suppose, in saying that okay, we only know of one way of iteratively solving, which is
Yeah,
to keep depressing, and this was a concrete indication that you might not well. You can't depress in this way, at least. So that suggests why it might be impossible. It wasn't like, oh, I'm not clever enough. I'm just going to think it's not possible. There actually
yeah.
was a concrete result that suggested that.
Exactly,
Yeah.
exactly. And it's the first thing that got people's minds thinking about the fact that maybe instead of trying to find a formula, you should try to prove impossibility. And
Mm-hmm.
that's a really meaningful shift in like the
Right.
productivity of mathematical
That's
thought
right.
once you
That's right.
start asking the right
Yeah.
question.
Yeah. Yep. 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 Yeah. Okay. Yeah.
Um,
So I want to see how this this non-existence of an orbit of the right size means you can't depress.
yes. Okay. So for that, I'm gonna remind everyone of the symmetric expressions that we had before. Let's say we were just doing it with like a cubic, just so I can write them all out. Minus R2, x minus R3. The coefficients that come out of this, remember we said one of the relevant expressions looks like the sum of all the terms. And
Mm-hmm.
this isn't specific to three. We could do this with any degree, but I'm just choosing one to be concrete. The next one looks like the sum of all the pairwise products. So these have a special name. They're called the elementary symmetric polynomials. Um, and like I said, they were in some sense understood, uh, the relationship between these and the coefficients since Viet, because he's the one that came up with them. But if we give these names for elementary polynomials, like E1, E2, E3, there's a very interesting fact that one paper I saw called it history's first whiff of Galois theory. And so it came up a lot before Galois. Um, first. I'll just first with, forgive the bad handwriting. I'm kind of
Okay.
speeding through here. Um, can't write well on my tablet either, but hopefully
So
people forgive.
I'll just put a T, I guess, first. Yeah. Okay. All right. All right.
Yeah, if you have any other symmetric expression of these roots. So for example, maybe I take something like r1 squared plus r2 squared plus r3 squared. And what I mean by symmetric is that no matter how I permute those symbols, uh, it will have the same algebraic value. So the ones we were just looking at were like almost symmetric expressions. So in this case, we want actual symmetric ones. The history's first whiff of Galois theory, which is also called the fundamental theorem of symmetric polynomials, um, tells
Mhm.
you that you'll always be able to express this in terms of the elementary polynomials, and in
Mm.
particular as some kind of polynomial of those. So it's
Mm.
a potentially confusing phrasing, but an example helps here, where in this case, if I took E1 and I squared it, if you think, okay, is that going to be the same expression? You'd say, well, almost, because when we square all of this out, we definitely get an R1 squared, an R2 squared, and R3 squared, but we also get a bunch of other junk. And in fact, what you get is exactly 2 times
Mhm.
E2. So kind of the correction term
Right.
here would be
All the cross terms.
minus,
Yeah.
yeah, all the cross terms. Um, and then similarly, if I had any other symmetric expression, um, and one set that Newton actually studied and understood pretty well is if you take these sums of the powers, he
Mhm.
had developed a system of formulas for how you can always express these in terms of the elementary symmetric polynomials. And this one is going to be a little bit harder to see offhand. Uh, I could look it up.
Mhm.
Viewers
But I
left
think,
isn't.
yeah,
It's going to start. You can
what
see
I
how
would
it's
do with
going to
like,
start,
right,
right?
E1 cube, you just kind of reduce the powers, right? Yeah, that's how it
Something.
would. Yeah. Yeah.
Um,
Yeah.
so
Is
the
the proof,
relevance,
yeah, is the proof hard? I mean, can you just like proceed by induction and do it by hand? I mean, that,
it's not the easiest thing in the world.
mm,
You can kind of proceed by kind of induction, but like what are you inducting on is a little bit
mm,
tricky.
mm,
There's there's a very good video about it in Chinese that I can pass along because it was a submission to like a math exposition contest I ran last summer. I
mm,
remember,
mm.
but uh, I can't think of like a nice two-liner way of describing
I
it.
see.
It feels kind of intuitive that
I see. But
maybe
at
it
a
should
high
be the
level, like
case.
is there, can you say like a word or two about like what's the key trick or insight, or is it not that simple?
It's exactly what you're saying. You do some kind of induction where
Okay.
you want to be able to reduce your sorts of like your expression might look complex in a certain way, like it involves a lot of kinds of things, and you
Hmm.
want to say, can I guarantee that I can factor certain things out so that each constituent part is less complex
Hmm.
in a certain sense? And then if they're less complex and you're like inducting on it, you can express each of those in terms of the elementary symmetric polynomials and then get it back. But
Mm.
what's the right like measure of complexity here?
Yeah.
Um,
Okay. Yeah. And maybe just so we have different levels of presentation. I mean, basically, just to formalize what you just said, basically, there's a there's a let's say, yeah. Well, actually, they're all algebra. The algebra of symmetric polynomials is the algebra generated by. We're working over reals or complex numbers. I'll just be more specific. Let's say complex numbers. It's the algebra generated by just these elementary symmetric polynomials, right? So it's basically you can. So this is an algebra. This is an algebra. And a priori, you have the inclusion of the right on the left because each of the EIs are symmetric, but the real theorem is that it's equality, that the entire algebra of symmetric polynomials is generated by just
yeah.
the E1 through En. That's like the formal way of writing it.
And for anyone who's a little familiar with Galois theory, you can maybe see why this is referred to as like history's first whiff of it, which is if imagine that you have some kind of field, see, and you adjoin all of the roots of a polynomial. And I'm basically saying, hey, I found an expression which, as I permute these roots, as I apply any automorphism to the field, which changes around those roots in some way, um, then this isn't a permutation. If you mix them up, then the expression stays constant. It's telling you that it's in the base field, or it's in the one that just had all of the coefficients. So here, I don't know. maybe I shouldn't be writing this as C. Maybe I write it as like Q, something where it's not necessarily going to have all of those roots, but it does have all of the coefficients. You're sort of saying you're able to write down this this new expression in terms of the coefficients, in terms of things in the base field, and it has everything to do with the fact that it's static under the symmetry. It's static as we permute all those roots. But like you said, proving that it's not exactly hard, but it's also not exactly trivial. Now, if we take that as a given, then look back to these expressions of Lagrange, it offers us a really interesting possibility where I'm going to say, let me give these names. So I'm going to call this one maybe capital A, call this one capital B, and call this one capital C. And let's say lowercase a, b, c, and d are meant to be the roots of, some degree 4 polynomial. So we would also write this as x minus little a, yada, yada, up to x minus d. And now I say, consider the cubic polynomial where these 3 different values are its roots. And maybe you can kind of see where this is going. And I'm going to write it just with a different variable, y, just to really emphasize that it is a distinct polynomial that we'll be looking at. Y minus b and y minus c.
So how did we go from this putative depressed cubic? Why are we stipulating that its roots are capital A, capital B, capital C?
Good question. So that we don't know what that cubic would be yet, and in fact, there's no reason to believe that such a cubic exists. And in terms of terminology, we call it a resolvent cubic. So depression just refers to when you take that next to leading coefficient and you make it 0. But then the resolvent is when you've actually reduced its degree in some way. Not necessarily reducing its degree. It's another polynomial such that the solutions of that other polynomial are a means to solving the original.
I see. Right. Depression relates to the original quartic. The resolvent is 1 degree lower. Yeah, sorry.
And I don't think I have that didn't answer your question of like, whoa, why are we suddenly assuming that these are roots of something? Mm-hmm. Instead, I'm saying, I'm not assuming they're roots of something. I'm saying, consider the thing that they are roots of. And now I want to ask questions about like, what's the nature of that thing? A priori, if you just take these 4 roots of the thing that we want to understand, they're probably complex numbers that have some difficult expression. We don't understand them. And if I said, hey, take 3 different things that you can express based on those 4 roots and make those roots of some polynomial, you'd be like, it's a nightmare polynomial. Its coefficients probably aren't even in our original field. You probably can't even write down the coefficients because they're in terms of they're just a hard to express thing in terms of the roots that we don't understand and we want to understand. But the beauty of them coming from these very symmetric things is that, like, think about now what happens if I say, what would this polynomial look like when we expanded it? So whatever the 4 roots are, it's possible to write these 3 expressions. Whatever those 3 resulting values are, it's possible to expand out this polynomial here. And what we're going to get is something where it's y cubed minus, we have the sum of a, b, and c is the y squared coefficient. Mm-hmm. But that sum a, b, and c is going to be a symmetric expression in a, b, c, d. So it's going to be something, I'll write this in like a different font, and maybe I'll write it as like S1 to connote. It's like a symmetric expression. It's some complicated function of A, B, C, and D.
Now. Yeah.
Right? Similarly, we're also, I should go back to my friendly red. We also have AB plus AC plus BC, all capital there, times Y. Again, it's going to be a mess if you think about it. Whatever this mess is, that is the sum of the pairwise terms of my capital letters, because it's a symmetric expression in the capital letters, it's also a symmetric expression in the lowercase letters.
Yep.
And then likewise for the final thing, which is the product. And I'll let you maybe finish the point for me. What significance does this have when it comes to what it means about this degree 3 polynomial.
The coefficients of our resolvent cubic are symmetric polynomials in the original coefficients a, b, c, d. Therefore, they must be functions of the elementary symmetric polynomials in the coefficients, and therefore functions of the coefficients of our original quartic.
Yeah, exactly.
Because the coefficients of the quartic are the elementary symmetric polynomials.
Exactly. And so here, actually, it would be helpful if I just actually wrote out some of those coefficients rather than leaving them hidden behind these dots, just so we can look at them and talk about them. But, this x to the 4 thing, it's got something that, let's see, I got that green color. We might call it a3 times x cubed, which is just a number. And then a2 times x squared, again, just some number. All of these are going to be numbers which determine what was the problem we were dealing with in the first place. The whole point now is that this new polynomial that I've written on the bottom, if we were to expand it out, like if we knew the roots already, and then we wrote all these things out, and then we expanded it and went through all that, we would find that it all reduces to something that could be expressed in terms of these coefficients. And actually, you don't need to know the roots already. If you just manipulate all of this, and then you apply, it's going to take work, but if you apply like the proof of the fundamental theorem of symmetric polynomials, you can figure out a concrete set of coefficients as functions of a3, a2, a1, and a0. It's going to look like a mess. They're going to be big, right? Like the y squared coefficient on this is going to be the sum of all those things. So you've got to like reduce all that out, but it's going to be in terms of the original coefficients, which means you can just plug it in. You just plug those in as numbers, which means if you know how to solve degree 3 equations, then you can solve for y in this whole system and get your 3 exact values for like a, b, and c. And then the final step is going to be to say, suppose you know a, b, and c. Suppose those aren't just like symbols representing these almost symmetric expressions. They're actual values that equal these. Can you use those to deduce what a, b, c, and d are? And this just takes a little bit more problem-solving massaging where, for example, if we assume that the sum of a, b, c, and d are 0, then that gives us a fourth equation up here, and this becomes a system of equations that we can then actually solve a little bit. So like, just for example on this, because it's maybe not entirely clear. If we assume that the sum is 0, which is another way of assuming that our original expression was depressed, that the a3 coefficient was 0, and we saw that's just a change of coordinates. You just substitute something in for x, and you can shift coordinates to make that 0. Then, for example, combining it with this expression, we have yet another instance of mean product formula, where I know the product of two values, these two parentheticals. I also know the mean of those two values, which is 0. And it would be enough to, for instance, tell you that a plus b and c plus d each look like plus or minus, the square roots of negative a, I think. Yeah, because that's something where the plus and minus square roots of that, if you should it be negative a or a? Okay, so it should definitely be plus or minus square root of something because we want their sum to be 0. And then the product should be a. So yeah, so I want the plus and minus because the positive square root of it times the negative square root of it will equal the negative of whatever that thing is. So in this case, we have an exact expression for a plus b or c plus d, which doesn't yet tell you what a, b, c, and d are, but combined with analogous things for the other ones, you can keep like pushing it around a little bit.
Okay, so at what point do we use the solution of our resolvent to get solutions of the quartic?
Great question. So given that the coefficients of this resolvent, these are just numbers. These are just things that we can express in terms, because we know what the coefficients of the others are. That means if we can solve degree 3 equations, that means we know what a, b, and c are. The big expressions, because each one of those is going to look like
Oh yeah, yeah,
that
yeah.
Cardano's formula we discovered earlier. So each one looks like this sum of two cube roots of things, but we know them. We can write down explicit values for A, B, and C.
Hmm.
And then the last, and that's 90% of the way there. To be able to write down explicit expressions for A, B, and C is quite the accomplishment. And the last hurdle is to say, now, is this system of equations the one where we know what the sum of all of the things are?
Ah,
We
I
assume that's
see.
here. And then we also have these three other equations, which they're not quite linear, but they're like they're asking to be linear. You know,
I see.
they're they're
So I think
gentler
this
than
should,
other.
yeah. So you start off with your degree n polynomial. You write down your resolvent polynomial, which has degree n minus 1.
Mm-hmm.
Then you apply your degree n minus 1 roots formula. I'm just writing this kind of abstractly. If you,
Mm-hmm.
supposing you had one, to get, uh, let's see, right, roots in terms of, well, the coefficients of the resolvent. Okay. So once you have those uh, roots, I'm trying to think. So, right. Okay. So those, yeah, maybe you could help me here. So I think I'm just a little brain twisted right now. Yeah.
I think this is the hardest part,
Yeah.
because there's not like it's not clear that there's a systematic way to do this, which
Mm-hmm.
is why it's the hardest part.
Mm-hmm.
Where I'm going to go back to slide 5,
Mm-hmm.
and then stop me if I'm just over explaining something or like
Mm-hmm.
pounding my head against something that we've said before. Imagine as a contest math question, someone has come and presented you with a system that's akin to the one on the right here,
Mm-hmm.
where you know capital A, B, and C,
Mm-hmm.
and then you're asked to figure out the lowercase A, B, C, and D.
Mm-hmm.
It's not obvious that you can solve this, but with a little bit of cleverness, you can maybe see how you would start to go about solving this. Where, for example, the first two equations are going to give you some concrete expressions for A plus B and C plus D, where they're kind of the same thing as solving a quadratic. You know the sum of these two, and you know the product of these two. Um, and I could continue writing it out if you want, where if you have something analogous to tell you what these two parentheticals equal and what these last three parentheticals equal, then if you just try like adding and subtracting them together in the right ways, you can get it such that you pull out exactly what A equals. And
Sure.
it's going to look like the sum of the square roots of two things. And
Mm-hmm.
then B is also going to look like the sum of the square roots of two things. And likewise for C. And with that, so like, I guess I'll just actually write kind of abstractly what things end up looking like. After you go through a bunch of logic, you get that A looks like the square root of something plus the square root of another something. And those somethings are like either A, B, or some combinations therein. Um, but the stuff on the inside is going to look like a cubic formula because
Mm-hmm.
that's where the capital A and capital B and C came from. But the only relevant thing here is that once we were to able to like we turned our original problem into a simpler kind of system of equations. Oh, no, erasing that. Like it's still the case that this is a system with four unknowns and four equations, which when we started off with the original degree 4 polynomial, as we saw with the symmetric expressions, you could write that as a system with four
Mm-hmm.
unknowns and four solutions, uh, four equations, but they're so nonlinear and awkward to work together with. Whereas this is like a much friendlier phase to get to. Um,
Ah, okay.
and where what I'm saying is not very convincing, and I just want to like bookmark and acknowledge that is this is a very specific case where it does happen to be true that with this new system of equations that emerged, we can solve it.
Yep.
And it involves basically breaking up each of these pairs of parentheticals and saying, okay, I can figure out what a plus b is. It's, plus or minus the square root of something. And then combining that, for example, with knowing what b plus d is, and then maybe subtracting out a plus d, certain combinations there, you can like filter out and just get an expression for a. It's not immediately obvious that you should necessarily be able to do that. Like, suppose you did answer Lagrange's puzzle and you said, I found an expression with five distinct variables that takes on four distinct values as we permute them. Mm-hmm. And then if I shift over to slide 7 and start going through your regiment, so that would give us a way to say, with those four distinct values that it takes on, I can write a resolvent polynomial, because the polynomial whose roots are those four distinct values is going to be something I can solve with a complicated degree 4 thing. And then I'll come back and say, great. So you have this almost symmetric expression that takes on four distinct values for the 5 permutations. If you knew what those values were as numbers, could you then recover what the 5 variables were? And in both of the cases that were relevant to what the Italians had done with degree 3 and degree 4, it was true that gave you a simpler kind of system that you could then solve. And it's, what I actually don't know if Lagrange had a way of saying necessarily systematically you'll always be able to take such a thing and then get the solutions from it. But at the very least, one of the steps that you're going to require to do that is that first one of finding an expression with 5 distinct values that takes on four algebraic values as you permute those 5 symbols. And if you can't even do that, then the second question is irrelevant. And he was struggling to even do that, to find such an expression. Turns out it's because it's impossible. We could cap off by showing why it's impossible if you wanted.
Sure. Yeah, actually, okay. I think I see the logic now that I looked back at that slide enough time. So let me try to just at least finish this off, so to close this story. So the point is, the coefficients of the resolvent polynomial are also themselves polynomial in coefficients of our original polynomial. Let's call this P. Right? And then the last step, and this one is the one that is questionable. It's true for 3 and 4, and the point is that 5 and above, this criteria of finding the appropriate orbit of the symmetric group doesn't even hold, so you can't even apply it. So it's sort of miraculous that this logic does work in some sense. So I think that was the part that was a little bit confusing. But the last step is to sort of say the coefficients of resolvent polynomial plus the depression condition is those are n equations and n variables, and you invert. And then then the last step is to invert. Okay, so I think that's let's for example go through this in the case of 4, right? So in the case of 4, what did you just do? You said, okay, n equals 4. We get a degree 3 guy over here. We're going to get 3 roots using our Cardano formula in terms of the coefficients of our original degree 4 guy. And then from those 3 roots, which are the A, B, and C. So this is the A, B, and C, right? We need to go back to, we need to recover A, B, C, D, which were the roots. You have, I guess, n minus 1 of these capital variables, and you have n of the small variables, which are the roots, and then you have the depression equation. Yeah, okay.
Can I zoom out for a second?
Yes.
I have to say, this is very elucidating for me. One of my questions going into this podcast was, how confusing is this really? I'm like, I have some conception. It was like a little bit, mind-opening to see Lagrange ask the right question. It's all muddled in the history. And zooming out, I think it's very complicated. It's like, there's kind of a reason, actually, that we don't introduce things this way. And it would be a bit of a mess. I do think the puzzle, even without the details of like why it's connected, this puzzle of trying to find an expression that has 5 variables and takes on 4 distinct values, I do think that actually is a nice motivating question. What I'm beginning to doubt in my own mind is whether it's worth the time to justify to somebody why that's a question anyone would ever ask, other than to like mention its historical significance,
Mm,
highlight the fact that like we can answer it, but it's a bit of a mess.
mm.
And like you're not at the end of the day, are you ever going to use this to solve a polynomial? No, don't, never do this. Like, just if you need to solve a polynomial, one of two things is true. Either you're in an engineering context where you want numerical solutions, and so you should use a numerical method. It's going to be like faster and more convenient than like the nightmare of radicals that you get here. Two is you're in a pure math situation where you want exact values. We should just define the root to be the solution of that
That's
polynomial.
right.
And like, that's what mathematicians just always do anyway. You don't need to write it with radicals to
That's
have
right.
a notion of it's you let the polynomial determine the properties of the root, not
That's right.
like some nonsense radical
Yeah,
expression.
that's right.
So all of this is only important for the history of it and not for what you'll do with it. So is it even worth, the headache of understanding what's going on?
All right. All right. Awesome. Okay. Great. 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 Okay. Well. Okay. Now this is that. Okay. This strategy is now clear to me, at least, in terms of how the parts line up, and the whole point is that the strategy works for n equals 3 and 4, surprisingly. And the last step is sort of, I guess, the surprise, because like this you just have to kind of do by hand, this last step, and okay, you do
Yeah.
it, right? That's the surprising step. And so the point is that for n equals 5, this is where this strategy fails. And so sorry, this strategy fails doesn't imply that the quintic is not solvable. That requires the whole whatever Galois theory machinery say.
Or
But at
Abel.
least it
Abel didn't
implies.
have Galois theory, but he
Oh,
came
oh,
up
I
with
see.
his own way.
Oh, I
Yeah.
came out. Oh, I see. I see. Okay, but this at least suggests why it's
Yeah.
impossible. Yeah. Right. Okay.
And
Okay.
it is a step in Abel's proof.
Okay.
That's another thing worth saying is that like the meat of Abel's proof does involve a thing that's effectively answering this question. And likewise for Galois proof. For anyone who has studied or has mentioned like, oh, you need to show that S5 is unsolvable, and usually involves some certain things and like the group theoretic meaning of the word unsolvable. The substance of that group theoretic unsolvability can be expressed in the context of thinking of like S5 acting on a collection of four things in this way, which I actually think is a much friendlier way to think about solvability than other proofs that I've seen. It's takes a little bit of connecting. It's not obvious like why the statement of decomposing into such and such normal group subchain yada yada is connected to the stuff we're about to do, but it is, and it can be. So
Okay. Where do we go from here?
let me see. I don't know if I'm capable of succinctness after doing everything, but let's see if we can try this.
Okay.
So
Yeah. I mean, let's try to get to the main result, right?
yeah. So this actually, I promise, should be conceptually simpler than the stuff we just did. So S5, is a way of referring to all of the different permutations that you might apply to a collection of 5 symbols. So, for example, if we just do some kind of swapping in there, that's one permutation. All 120 different permutations we collectively call S5, or more specifically, that collection combined with the way of composing 2 together, and that being like a structure we put onto this set where you can combine 2 to get another permutation. Now, the question is, suppose that we had some magical expression, which, I'll call E, that equals, it's some kind of function of these 5 things, A, B, C, D, E. And our hope is that, maybe I'll call it E1, that as we permute the 5 different variables, it only takes on 4 distinct values. And here's the basic idea. I say, consider what happens when you apply a 5 cycle to the variables. So for example, something where A goes to B, B goes to C, C goes to D, D goes to E, and then E goes back to A. So it's a permutation such that you have to apply it 5 times in a row before you get back to the identity. What would happen if this is acting on only 4 symbols, E1 through E4? And you might say, well, could it be the case that one of those symbols has an orbit with degree 3? Maybe E1 goes to E2, that goes to E3, and that goes back to E1. They say, well, that couldn't happen, actually, because after we apply our 5 cycle, which I might even give a name and call the the action that's applying all of that sigma
Hmm.
sub 5. When I apply sigma sub 5 times, it wouldn't have acted trivially on my e's
Hmm.
because, if this only has a period of 3, it'll end up somewhere else. But of
Right.
course, all the original symbols got back. Um, Nor could these have undergone a 4 cycle, something where the orbit of E1 like traverses over 4 different things. Um, and uh, let me actually make sure that what I'm saying, what I want to say, yeah, okay. I think I'm comfortable saying this. Any 5 cycle has to leave all of these expressions static.
The only way that uh, sigma 5 can act on a four element set is to fix every one of those elements, right?
Yeah. Um,
Or another way of saying it is the orbit has to be of size 1 or 5, and on a four element set, uh, the orbit can only be size 1. Yeah.
yes,
Yeah. Okay.
exactly.
Yeah. Hmm.
So all 5 cycles have to leave that fixed. Next statement um, is a little bit harder to. Okay, so some permutations are even and some permutations are odd. Do we want to define the notion of an even permutation? I guess
Uh,
it's not that hard,
no, it's
I
just
guess.
yeah, it's
Yeah.
just the number of transpositions that you can
Yeah.
express it as, right? Yeah.
So any permutation that you write, you can write as a collection of transpositions. So, maybe it's like A swapped with C, B swapped with D, D swapped with C.
Hmm.
Just a succession of swaps. And when there's an even number of such swaps, we say the permutation is even. When it's odd, it's odd. The non-trivial thing there is that if you have two distinct ways of writing a given permutation as a set of transpositions, do they
Yeah.
necessarily have the same parity? It's
I,
not obvious, but it
yeah.
is true that they have
Well,
the
here's
same.
one. Now that I just on the fly, it's like one way to make this obvious is to write the permutation as a matrix, a
Hmm.
permutation matrix. Like think of it basis elements, and then it's the whether even or odd is just the sign of the determinant, and then it's obvious that there's no like that's
Great.
just well defined, right? Yeah.
Great.
Yeah. Okay. Yeah.
Much better
So
way
that's
to do
another
it.
another way you could do that. Yeah. Hmm.
Okay. The subgroup of even permutations is called A5.
Hmm. Right.
This is subgroup. Um, this is all of the even ones. So this has 60 different elements in it. This one has 120.
Hmm.
Um, all of the 5 cycles actually generate A5. And so that one is a little bit less obvious to show. But basically, if you wanted to prove that for yourself, the way to show it is that um, any transposition is possible to express as a product of 2 5 cycles.
Mm.
And so just a little puzzle. Can you find 2 5 cycles that you compose them one after the other? You
Mm.
get a transposition, and that you can
Mm.
do that for any transposition.
Mm.
Once you have one, you have them all because you can just relabel whatever expression you just wrote here. Um,
Hmm. I see.
so if
I see.
instead of you wanted to swap A and C, if you wanted to swap B
I
and
see.
D.
So A5 is just this could be written as the subgroup generated by all 5 cycles, right?
Yes.
Okay.
So in particular, anything from A5, not just the 5 cycles, but anything from A5 leaves all 4 of these symbols fixed.
Mm-hmm.
Um, great. Uh, and then what's our what's our thrust from there? So the only things that could possibly move any of the like act non-trivially on our 4 expressions would be um, transpositions
Mm.
or things with odd parity.
Mm-hmm.
Now, why would that necessarily make it impossible?
The orbit has to be the entire set, right? Is that?
Yeah,
Uh-huh.
yeah,
Yeah. And so there's no way you could have a transposition, which is order 2,
right.
right?
Okay.
Act uh, whatever transitively.
Sorry, maybe I'm being a little bit slow here. So I can see for a particular element of S5 that's odd, you might say maybe
Yeah.
it does something that just swaps 2 of them. Um, and so, but how do you know that it's not possible that some other odd permutation like swaps another 2 of them so that the orbit of E1 um, under all of S5 like actually
Because
goes
I
to
think
everything.
basically S how to say uh, S5 mod A5 is just a two element set, right? So since we know
Yeah.
that A5 fixes the entire set, to know the entire orbit under S5, you just have to know, you just pick one non-trivial element
Yeah. Okay.
and see how it acts, right? So in other words, the action of S5 factors through the quotient S5 mod A5, right? And S5 mod A5 is just going to be a two element group, just Z
Yeah.
mod 2. And
Yeah.
there's no way Z mod 2 could act on this set such that the entire orbit the entire
That's
group, because
exactly right.
right,
Yeah.
because
So thinking of the quotient group there.
yeah, exactly.
And I
So
guess
let me yeah, yeah,
oh, the
yeah,
one thing I
exactly.
wanted to highlight there is
Hmm.
like to articulate that you did have to like speak group theory. You had to
Hmm.
talk about the quotient group and what factors through and things like that.
Yeah.
So
I mean, in this case, it's a little bit easier because you could just say basically every permutation can be written as a product of an even permutation and a transposition. And we know that all the even ones have to act trivially. And so you just have to know what like a transposition does, right?
but if that's all that you said, how would you know that you don't have multiple different transpositions that act differently? Like, that one transposition, does
Oh,
one thing to your expression and another.
because one transposition will differ from another transposition by an even permutation. And we already know
Oh,
that
yeah,
that
because
fix.
if you apply them back to back, then it's an even permutation,
Yeah.
which has to do nothing. So
Yeah.
therefore they have to be the same. Okay.
Yeah. That's the point.
Yeah.
Yeah. Yeah.
Yeah.
Yeah. Yeah. Yeah. Yeah.
Um,
Yeah.
yeah, there you go. So that answers Lagrange's puzzle. That tells you why you can't have, in the same way that for 3 and 2, we could discover these resolvents by writing down these algebraic expressions that, let's see if I go back where, in the case of 3, I can write something that has 2 distinct values, 3 variables. With 4, we can write something that has 3 distinct values, 4 variables. The thing that goes wrong at 5 is now there's too many prime numbers available.
Mm.
Why does it stop at 5? Like why 5 and not anywhere else? It's like because 5 is 5 is the first time that you have 2 different odd prime numbers at odds with each other
I
in some
see.
sense, right? Because the even subgroup is usually generated, or it can be generated by all 3 cycles. And in this case, it was also generated by all the 5 cycles. And those sort of, yeah, the fact that it was generated by 5 cycles ran over the fact that we wanted it to be acting on a thing with only 4 elements. And so those 5 cycles had to be acting trivially on it.
Mm.
And that was just too much of a constraint to handle. Whereas with S4, for example, it's fine. Because you say, oh, what happens when we act with all the 4 cycles? There's no, those aren't generating some special subgroup in the same way. So you don't run into that same kind of paradox. Okay, so long-winded way of like getting to all that. And so once those are the ideas in your mind, again, like zooming out to say, like, why wouldn't we care? What is the point? The first thing there is like realizing maybe the right question to ask about these polynomials is if it's not even possible to solve it. Because clearly we've demonstrated something different happens at 5 that wasn't happening. We haven't shown the unsolvability, but we have shown that something different happens. And second, the way that we showed it had everything to do with permutations and understanding not just like what are the permutations, but how do they compose with each other? The conclusion, we're like, this 5 cycle, you compose it with itself 5 times and nothing happens. These 2 cycles, you get one after the other, you have an even permutation. It's all about the compositions. With those ideas in mind, like if you find yourself as this young teenager thinking about quintic polynomials, having read Lagrange, then it doesn't seem as coincidental that you are the one to discover that they're unsolvable and bring that proof to fruition. Because it happened twice in history. Because Abel did it when he was a teenager, and then Galois did it when he was a teenager. Abel might have been like in his very young 20s at university or something, but both of them, like very young, they did it. I think Galois, in his own words, he was originally like unaware of Abel's work. Of course, later he became aware of it, but when he first started thinking about it, he didn't know.
So how did Abel? Okay, so we what this analysis just did was rule out the approach that Lagrange proposed and suggested it was unsolvable. That this doesn't prove the unsolvability of it. What did Abel do?
Yeah, because what
above
you
and
have,
beyond?
Yeah, what you have to do is say, assume that you have a formula that solves these things.
Hmm.
Um, is it necessarily the case that that formula that's going to have some outermost square root in it, maybe that outermost root, like fifth root or something? Um, can you show that implicit underneath that is the existence of something like what we just did, where in order to uh, how do you phrase it? As you have that formula, you're thinking of it as like building up your roots from simpler expressions that start at the coefficients, and then you're putting radicals around them. But another way to think about that is you're sort of adjoining on roots of specific little polynomials. Like anytime you add a cube root of something, you're adding on the solution to an x cubed minus c
Hmm.
type polynomial. And you have to say that this tower that you get, I'm not sure actually if he would have phrased it in terms of towers, because the version of his proof that I read was definitely like a brushed up for modern eyes in
Mm.
terms of like how to express it. But you want you want to show why that is why the intermediate steps that you get along the way for that necessarily have to satisfy these kinds of
Mm.
conditions where the way that you're acting on them, you know, uh, uh, I would need to actually look at it again to remember properly. But the one relevant fact I can remember is that this is not wasted work. That this part of the proof that we did here, it's not just saying, okay, so that tactic is irrelevant. Now let me do something completely different.
Mm.
Like this assessment of 5 cycles generating all of the even permutations, bringing you to the final conclusion about what must be true. Like that carried over very directly
I
um,
see.
into the proof he did have. But I don't remember the details, to be honest.
I see. Because okay. Because I mean, we're not gonna have time to go into it, but I guess we could just say it in words and maybe provide a reference. But there's a topological proof, I guess, due to Arnold, and what I like about that proof is uh, it's visual, and there the group action is in terms of what mathematicians call monodromy, right? Uh, I'll just say very brief on this. The way you can think of monodromy is already when you write the quadratic formula, right? You had this square root of b squared minus 4ac, and the point is when you take a square root, when you start moving, when you think of the square root function as a quote unquote function in the complex plane, it's not single valued. It's actually multi-valued in the sense that, well, it's in the sense that you have two solutions, but also if you try to continuously uh, move the argument of the square root around in the complex plane, you'll actually end up at a different solution, right? So in other words, if this is the complex plane and you try to define the square root of z, then you take the square root of 1, you define that as 1, but it turns out as you move around, you're going to go from 1 to -1, because basically a square root halves the angle components of your complex number, and so when you go 2 pi around, you're only going to go pi, right? And so there you can already think of this as being sort of a z2 action, because really what you have are two roots uh, sitting over the complex plane. So you think of the square map, z goes to z squared, the square root's the inverse function. You have these two choices, and sort of as you move around, then what monodromy is that these two solutions get permuted, right? So basically, you can think of group actions in terms of this uh, uh, the monodromy group, essentially, right? And it's beautiful in terms of just moving points around and thinking of covering maps. Um, all this was to say is that, first of all, there is a very beautiful proof I didn't know before and learned about in leading up to this. But the question I wanted to ask was, it's not obvious to me the way you describe Abel's proof why group theory even shows up. There was group theory in Lagrange's purported proof, but at some point Abel uses it again in a different context.
Well,
Where does that group theory kind of come from?
I guess critical is that group theory didn't exist, right? The first person to use the word group was Galois, and the first
Or I
person
guess
to
implicit, yeah.
and the fact that it's implicit also kind of means it has to be simple, right? It's
Mm,
not going to be complex ideas. So the
mm,
way that it comes up is just insofar as he's saying you can, when you combine two different 5 cycles, you can find a way to do so that will generate any 3 cycle, and then from that get you up. Oh, so I think
uh,
I think I miswrote things a little bit earlier. It's not that you can it's not that you can combine any two five cycles to get a transposition, because that you actually can't do. It's that you can combine any two five cycles to get a three cycle, and then you want to be
Right.
able to say why any combination of
That makes sense. Yeah. Maybe we should also state a fact that starts at like an n cycle uh, is equal to what I think it's like n plus one transpositions, or it's certainly, or sorry, it's going to be uh, even if n is odd, and odd if n is even. And so of course a three cycle is even. You can't, the product of even permutations remains even. So there's no way you could have had two five cycles equals a transposition,
yeah.
which is odd. So yeah, it makes sense that you can get a three cycle. I mean, that follows from this A5 thing, because A5 is all the even guys. A three cycle is even. And well, it's generated. Oh, sorry, it's generated by five cycles. I guess the one computation you have to check is that you can get away with just two. But I think the argument probably applies even if you had multiple, right? Like two isn't special in this regard, is it?
Yeah, the
Yeah.
relevant thing is that with the five cycles, you sort of get half of the whole group. You might think you get many few, but you get half of it. Or
Mm-hmm.
I think even in the way that he was doing it, might have been the relevant thing is how you can combine two five cycles to get a three cycle. You can also combine two three cycles to get a five cycle.
Mm-hmm.
And that pairing
Mm-hmm.
can like give you the impossibility that you want. Um, because essentially, like in his proof, he's sort of saying he's the shape of it I remember is like if you had some kind of formula for it, he shows why the innermost expression would have to be a square root.
Mm-hmm.
And from our like modern lens, we can see that corresponds to the fact that the first like normal subgroup available to S5 is A5, and the
Mm-hmm.
index there is 2. But he shows like in whatever magical expression you came up with, the innermost thing would be a square root. And then he proves why the next level must be a cubed root. But he also proves why the next level must be a fifth root. And that's the contradiction. And the way that he gets it kind of in both his cases, like because three cycles generate, he didn't phrase it this way, but
Mm-hmm.
basically because three cycles generate A5, that next level must be a cube root. But he also shows five cycles generate A5, so that next level must be a fifth root. Um, but is that group theory? Like, is the statement that uh, half of all of the permutations of um, five symbols can be accessed by stringing together five cycles? Like, yes, it is. He's not using the words generator, and it's not using the word subgroup. He's not using the word group at all. And I think a big part of the insight that Galois brought that Abel didn't is the recognition of just how valuable it is to abstract away like that. And he was like, rather than just thinking in terms of permutations in this whole mess, I'm just going to call this thing, I'm going to give it a name. I don't even know what to call it. Group. Terrible name, but why not? Just group, right? And then say, what can I ask about that kind of thing? And he definitely had an attitude that was much more like wanting to pull out as much as he could so as to avoid the complexity and just look at the distilled, clean version of the argument itself. Even still, if you look at Galois stuff, it's very messy and kind of hard to follow. But
Mm-hmm.
for what it was and for his time, um, and so it it doesn't necessitate inventing group theory in order to answer this question, but it makes it a lot easier to answer when you do. And the whole reason that we care about it is because this was the first moment that someone thought to actually do
Right.
that. That someone wasn't Abel. He was close to it. Had he lived longer, he might have gotten to it too. Because in his quest to understand the more refined question of which equations can be expressed with radicals or not, he effectively recognized the significance of an abelian group. He didn't call it that. That's maybe why we call it that, right? But he was talking about, oh, when you do these substitutions, if the order doesn't matter, then from there we can like get out an expression that we want. It's a highly non-obvious result. And so, I mean, like I said, he died when he was 26. He's very smart. You do have to imagine you just keep drawing out that line a little bit farther. Where would he have been if he had lived into his ripe old age? If Galois hadn't beaten him to it, it seems a safe bet he might have invented it.
Mm-hmm. Maybe just to push on this a bit, but one last thing, because I think the thing that was tricky, the most tricky part in this proof of the unsolvability of the quintic was exactly what this point we're talking about in terms of three cycles being two five cycles, or two and getting five cycles from three cycles. From the topological point of view, you can think about it in terms of like, well, roots kind of tell you how what the monodromy looks like. You know, if you had degree 3, degree 5 things, then you now have 3 possible roots or 5 possible roots, and you can imagine for complicated polynomials in general, you could permute them however you want as you move around, and then you start getting contradictions based on, you know, um, uh, basically consistency relations in terms of that monodromy, right? And I think uh, I could sort of intuit it, but I can't give a kind of a like a razor sharp argument about what these constraints or abilities of cycle compositions implies about a contradiction at the level of monodromy. But I think that's so that's ultimately what's happening, right? At least at the topological side. I think of the algebraics, I have a hard time kind of getting a sense of what's going wrong with the algebra, with you know some relations between cycles. I don't know if there's anything clarifying you could say about that, but I think for me, my biggest gut feeling of why these cycle relations imply a contradiction is in terms of some kind of inconsistency with trying to define monodromy.
Well, it's hard though, because the way that Arnold does it with his monodromy proof there is that it's he's thinking about uh cycle commutators
Mm,
and the structures that come
mm,
about. If you look at all things that look like A, B, inverse A, inverse B,
I see.
um, and basically gets like a nice correspondence between those and then what has to stay fixed for a given radical that shows up in your proposed expression. But what that means is to disprove the possibility of a formula that layers these radicals together. Like actually you can be very expressive with your layer if you have an expression with layers of radicals. And so it's to me at least not immediately obvious that the expressiveness that you're able to have with like very layered net radical expressions isn't enough to do something like S5. Um,
Exactly. Yeah.
uh,
Yeah.
and the way that he shows it ends up being that when you look at the commutators of the commutators of the commutators, which is a very complicated thing to think about. And that's the hardest part of his proof. If you're not already like a group theorist, you're not already like tuned to think about a commutator subgroup, um, then it does give you the contradiction that you want. But what I like about the Abel one is if someone just sims out and says what group theory is used, at its barest bones, you can say compose 2 5 cycles, you get a 3 cycle. Compose 2 3 cycles, you get a 5 cycle. That is the fact. That is the group theoretic fact, and everything else,
Mm,
you don't need group theory. You can follow. With
mm,
Arnold's in the topological one, you say, what's the group theoretic fact you use? You're like, well, it's that the commutator subgroup of S5 is its own commutator subgroup. And it's like a harder statement to say. And you could try to parse it a little bit. You could say, oh, it's because you can find a commutator of 2 uh, expressions of such and such form that is another one of that same form. Like you can get it a little bit simpler, but there's not going to be as clean a statement. And I remember taking a long time to think about can I modify Arnold's proof to be to use the group theoretic fact of Abel's proof of just this relation between 3 and 5 cycles. And basically I got something that was like pretty close and like does use that, but it's at the expense of making another part of it more complicated. And so it felt like playing whack-a-mole. And ultimately I decided the Arnold proof was just actually the simplest one. But uh, that is, I think, sort of its I won't call it a shortcoming, but it's the one part that I really wish if I could get that in there, then it would be like the most fun video to make. Where
mm,
if you use the group theory that's as simple as Abel's, and then the connection to formulas, which is as visual and beautiful as Arnold's, then
mm,
that would just be like such a great love child proof. And I tried for a while, and I just didn't get it, I think.
mm. Okay. Well, I guess yeah. Thanks so much for this very nice hands-on discussion of the unsolvability of the quintic. It was certainly a good way for me to revisit this fact. I remember having taken Galois theory way back when I was an undergrad. I've forgotten all of it since I never used it, but I never had a how do I say? One of the downsides of abstract math is that even if you learn it, there can be a very big disconnect between that and giving like something that's very intuitive and simple and minimal, so to speak. And I think this kind of analysis was very helpful in kind of getting like what do you actually really need and what's kind of really going on with your bare hands, so to speak. So I think this is very nice to discuss.
hopefully it makes up for the fact that we didn't actually prove the unsolvability of the quintic after 3 hours.
Okay, but I guess this video will be a good way to motivate people why they might want to study
I think it
Galois
motivates it,
theory.
hopefully.
Yeah,
Yeah.
great, great. Well, yeah. Well, thank you so much for your time, Grant Sanderson, and we definitely look forward to more of your beautiful math videos.
Yeah. Thanks for having me on.